Hi, my name is Phil, and I'd like to wish Time a happy 20th anniversary on the Science of Synthesis series, which has been an essential part of our laboratory's library for a very long time now. We use the online version, we use the text one, as you can see right behind me. And it has been a really integral part, at least of my life, in the way I go about brainstorming for projects in the laboratory, finding literature which is sometimes very obscure and hard to find on SciFinder, or for solving very difficult consulting problems. So I'm really grateful to Time for putting together this amazing series and continuing this wonderful tradition. It's a huge help to the community. Fantastic trove of information which you may not be able to find anywhere else, and it's so beautifully organized, and thank all the contributors over the years for their diligence and hard work in putting this together. And I wish you all hopefully another 20 or 30 or more years of great success in putting this series together. Happy birthday.
Hi, my name is Margaret Fall. I work at Amgen, and I've been a member of the editorial board of Science of Synthesis since 2018. I would like to take this opportunity to congratulate Theme Chemistry and the Science of Synthesis on their 20th anniversary, and to thank the Theme and Science of Synthesis team, the editors, and all of the authors who have contributed through the scientific community through the publication of this journal. As you're aware, the Science of Synthesis occurs in both hard copy and online versions, and for me, I find it's really well organized and it's easily searchable. It provides critical reviews of organic chemistry transformations, but also a feature which I particularly like is it provides the detailed experimental procedure for performing many different reaction types, which is extremely valuable whether it's a new chemist starting in the lab or an experienced chemist that's working in an academic or an industrial setting. Science of Synthesis over the last 20 years has truly become that foundational single source of truth for organic chemistry transformations, and has been an amazing contribution to the scientific community. With that, I congratulate you on your 20 years. I wish you the best, and I look forward to many exciting contributions and many additional contributions in the future.
Hi, this is Shuli Yu from SLC. This year will mark the 20th anniversary for Science of Synthesis. I would like to congratulate to Team Chemistry for doing such a great work over the years. Science of Synthesis is a unique reference work which covers all methods of organic synthesis, offering the full text descriptions of organic transformations together with validated experimental procedures. I really like this feature, which saves us a lot of time during our research. The online version is also really amazing and entirely searchable based on the structures, substructures, and reaction types. I was fortunate to join the editorial board of Science of Synthesis early 2018. I would like to thank the Team Chemistry team, all the editors and authors for their hard work. I wish Science of Synthesis keep doing great and maintain such a high level of excellence in the years to come. Happy 20th anniversary, Science of Synthesis.
Hello everyone, and welcome to today's virtual symposium in honor of Professor Barry Trost, which has been organised on the occasion of the 20th anniversary of Science of Synthesis. My name is Fiona Short and I'm the Managing Editor for Science of Synthesis at TIMA. Today we are going to celebrate the career and achievements of one of the finest chemists in organic synthesis, Professor Barry Trost, together with some of his former group members, themselves very highly respected and acclaimed chemists. We have been overwhelmed by the response to the symposium with over 2,250 registrations. Before we get started, I'd like to go over a few housekeeping items so you know how to participate in today's event. Please note that this web seminar is being recorded. A link to the recording in YouTube will be sent to all registrants shortly after the seminar via email. The link will expire after 2 weeks. The audience will be kept on mute during the web seminar. At any time during the symposium, you will have the opportunity to submit your questions to today's speakers. To do so, just type your question into the chat window. Please note, though, that unless you choose the anonymous option, your name will be visible to the panelists and may be mentioned. The chat will not be open as such for general discussion because of the large number of attendees today, which I'm sure you appreciate. As many questions as possible will be answered live after each scientific talk, and my colleague Dr. Alex Russell, Senior Scientific Editor for Science of Synthesis, will be on hand as chat manager and will help in the choosing of questions for the moderators and panel. Please look out for the free content and trial information as well as useful links that we will post in the chat window during the course of the symposium. And please tweet at Team of Chemistry and hashtag SOS20years. My colleague, Dr. Toby Reeve, Senior Scientific Editor for Science of Synthesis, will be tweeting for us this evening too, and is ready to engage in a conversation with you. For those of you not familiar with us, Team of Chemistry specializes in the field of organic synthesis, and many of you will be familiar with some of our journals, Synthesis and Synlet, as well as our reference works, Huben Weil, Science of Synthesis, and indeed some of our monographs, for example, Kuczynski's Protecting Groups. During the course of the symposium, you will have a chance to learn some more about us. So just looking at the agenda looks like this. So we'll have 3 talks from Professor Cossy, Professor Maulide and Professor Lautens of 25 minutes each, followed by Professor Trost's talk of 45 minutes. And we will be holding a 10-minute break after the initial set of 3 talks, so you can get some refreshments. I would like to now introduce both our symposium chair, Professor Gary Mollender, and Editor-in-Chief of Science of Synthesis, Professor Alois Fürstner. Professor Gary Mollender is the Hirschman McEnany Professor at the University of Pennsylvania. He received his BS from Iowa State University under Richard LaRocque and his PhD with Herbert Brown at Purdue. After a postdoctoral stint at the University of Wisconsin-Madison with Barry Trost, he began his independent career at the University of Colorado Boulder before moving to the University of Pennsylvania, where he served as chair from 2009 to 2018. His research interests are in the development of new synthetic methods. He has won many awards, including the ACS Herbert C. Brown Award for Creative Research in Synthetic Methods. Within the Division of Organic Chemistry of the ACS, he has served as member at large of the Executive Committee, Secretary Treasurer, and Chair of the Division. He was also the Executive Officer of the National Organic Symposium, is co-chair of the Division of Organic Chemistry Graduate Research Symposium, and is a Fellow of the American Chemical Society. Gary has been involved with the Science of Synthesis project since 2004 and is a member of the editorial board since 2008. He has been responsible for numerous volumes as a volume editor and helped greatly with author and volume editor acquisition for the project over the years. He is a very highly respected and trusted editor with whom my team and I have the honor and pleasure to work with. Without Gary, this symposium today for Professor Trost would not have been possible, and he has gone to great efforts to help with its organization and the invitation of our wonderful speakers. Professor Alois Fürstner is a native of Austria and obtained his doctoral degree from the Technical University of Graz. After a postdoctoral stint at the University of Geneva, Switzerland, and a habilitation in Graz, he joined the Max Planck Institute für Kohlenforschung in Mülheim, Germany, as a group leader in 1993. In 1998, he became director at the institute. His research interests in the area of organometallic chemistry and homogeneous catalysis range from the characterization of reactive intermediates and method developments to applications in natural product total synthesis. He has many honors, including the Tima IUPAC Prize, the ACS Arthur C. Cope Scholar Award, the Carl Ziegler Prize, and the ACS HC Brown Award for Creative Research in Synthetic Methods. Alois has worked on the Science of Synthesis project as a member of the editorial board since 2008 and has also been responsible as a volume editor in the past. He became the first editor-in-chief of Science of Synthesis in 2017 and has made some important international appointments to the editorial board. Alois has also helped to set up the Dr. Margaret Fall Award for Women in Chemistry and chairs the selection committee together with Dr. Margaret Fall. The Science of Synthesis team and I have the honor and pleasure to work together with Alois, and we are very appreciative of his continued help and support for the project, as well as his advice and guidance. So without further ado, over to you, Alois.
Ladies and gentlemen, first and foremost, I would like to extend a very warm welcome to all of you, the speakers, the panelists, and of course, to all other participants, wherever you may join us. As you have heard, I'm currently the editor-in-chief of Science of Synthesis, and it is in this role that I would like to say a few words about Science of Synthesis itself, and also about the reasons why we are holding this virtual symposium today in honor of Professor Barry Trost. I suppose that many of you are familiar with Science of Synthesis, published by Thieme publisher here in Germany anyway. As the name suggests, Science of Synthesis is, I believe, a truly unique source of information, providing an encyclopedic coverage of all aspects of organic and organometallic chemistry broadly defined. It does contain information on no less than 2 million molecules and something like 430,000 different reactions and probably more than 50,000 experimental procedures. Now, if you now think that Science of Synthesis is nothing else but yet another big database or search engine, then you really miss the point. In its inner structure, in the way the information is presented, Science of Synthesis differs fundamentally from other databases that you might be familiar with. Other than these competitor databases, Science of Synthesis does not even intend to collect each and every little piece of information. Rather, Science of Synthesis wants to commission quality content from expert authors and intends to provide the user with a pre-evaluated information. It is the expert author's duty to keep the rubbish out while making sure that each particular method with a meaningful and a reasonable scope is thoroughly and properly covered, critically assessed, and presented in a clearly structured and logical manner following the concept of the functional group with which we are all familiar. So let me give you an example. For instance, you have to make a particular, say, pyridine derivative, and you do your search on one of these standard search engines. That might easily give you 3,000 or more hits, some of which may turn out actually not to be hits. But how do you know? So either you take the time and go through the entire list one by one, or you restrict your search and take the risk of missing the one reference that really matters for you. When you do the same kind of search with Science of Synthesis, this time-consuming task of sorting out the information that is likely going to be relevant has already been done for you by an expert who knows the particular field well and who has written and compiled the corresponding chapter. Therefore, it is much more likely that you will be directed to those methods that really matter, that are deemed reliable, and that do have a meaningful scope. And this scope is then clearly laid out for you in the text, in the schemes, in the tables, and the accompanying procedures give you an immediate impression of the practical aspects of a particular method. And of course, if you then want more information, you are also directly linked to the original publication. So in a nutshell, Science of Synthesis is, I think, a truly unique combination of expert knowledge and a large database that does contain the necessary detail. Oh, here it is. That does contain this necessary detail. And this particular combination is what can save you tremendous amounts of time and effort. So I personally sincerely believe that science of synthesis is the place to begin when writing a thesis chapter, when writing a grant application, when preparing your next seminar presentation, or when preparing a consulting session as well. The high standards of science of synthesis are stipulated by the board of editors, consisting of 9 highly renowned chemists from America, from Asia, and from Europe. And you can see the faces and you can read the names on this particular slide. The editorial board represents the older and the younger generation, female and male scientists, academia as well as industry. And we do think of this diversity as a real asset. Now, the board is supported by a very professional team in charge of science of synthesis at the publisher house Thieme. Most of them are PhD chemists themselves, and most of them are English native speakers. So they do understand the scientific content of the chapters they are editing. And at the same time, they are able to make sure that the language also complies with good standards. Now, of course, I know that you will think, oh, he's the editor-in-chief, so it is his duty to make science of synthesis great and let it shine bright. What else would you expect from the editor-in-chief, right? So if you do not trust my word, just let's have a quick look at what other people think about it. Everybody, I think, knows this gentleman. Now let me read for you the opinion of Professor Noyori, Nobel laureate, but also one of the founding members of science of synthesis. Here is what he thinks. Today's scientific community must struggle to find ways to effectively distill massive floods of information into real knowledge. Science of synthesis does this superbly well with carefully selected content on synthetic organic chemistry that has been written and edited by leading authorities from around the world. Science of synthesis is a must-have for all universities and research institutions involved in material synthesis. Here is yet another voice, this time from the younger generation. And I think, again, Professor Barron needs no introduction. But let me emphasize that he has not been associated or affiliated with science of synthesis in any official way, yet here's what he thinks. Science of synthesis is an indispensable tome of chemical information, organized in an intuitive and logical way. It contains information on nearly every aspect of chemical reactivity, and for me, is the go-to resource for rapidly learning about a new area. I use it regularly in preparation for classes and for consulting visits. It simply gives me the information I need far more easily than any search engine is capable of, and very often contains references and insight that cannot be found anywhere else. And I could go on and on, but please take a minute and find out yourself what the really young generation, the upcoming next generation, thinks about science of synthesis. You will find a number of vignettes that shows their experience and their opinion about this research tool and this research tool. So, needless to say that the interface and the search engines behind science of synthesis, the electronic version of science of synthesis, are state-of-the-art and I think also pretty intuitive. Of course, you can search for text, for structure, for substructure, for keywords with the tools that you are probably familiar with anyway. And by the way, since science of synthesis is not just a random compilation of data, but has a logical inner structure, You might even find the good old concept of the table of contents useful. You must make an author ester and you don't know how? Well, maybe 2 or 3 clicks will take you there, and 15 minutes later, believe me, you will have a pretty good overview over the state of the art. And of course, you can find additional resources on the internet, the usual YouTube videos, and I would in particular point out to you these web seminars in different languages, including Chinese, Japanese, and Hindi, and Portuguese, and Spanish, and French, etc. Now, you must also know that science of synthesis works through institutional subscription. So if the university or the company you are working for does not subscribe yet, you can sign up for a free trial on the Thieme homepage. And I'm convinced that if you check it out yourself, you will almost certainly find science of synthesis an extremely useful and at the same time a very convenient tool to work with. That brings me to the final aspect that I want to emphasize. Science of synthesis strives for quality and cares about the science. And this explicitly includes the scientists. Satisfaction amongst the more than 2,000 authors and volume editors who have worked for science of synthesis during the last 2 decades is overwhelmingly high. And believe me, this list does include a number of very eminent authors, including Nobel Prize winners. We are also very proud of having launched a new award, a forward-looking award, named after Dr. Margaret Fall, Executive Director, Process Development of Amgen in the United States. And Margaret is member of our board of editors. The Women in Chemistry Award is meant to bring role models to the attention of the younger female scientists in order to encourage them to consider a career in chemistry. The first recipient was Professor Sarah Riesman from Caltech. And there is a special issue of Synthesis, also published by Thieme, in the pipeline to commemorate this event. And before I forget, the call for the second Women in Chemistry Award is currently open. So you still have time to nominate a young female colleague who is in the early stages of her independent career until December the 11th, I guess. So exactly a month from now. And again, you will find more information on the internet. Now, I just said, science of synthesis cares about the scientists. And there is one person who science of synthesis really owes a lot. And that is Professor Barry Trost, known to all of us as one of the most eminent and most accomplished chemists of our times. Professor Trost was not only one of the founding fathers of science of synthesis when this project started 20 years ago, but he's actually the only of the founding members who still actively serves on the board. For his vision, for his leadership, and if I may say so, for his incredible and literally encyclopedic knowledge of organic and organometallic chemistry, he has shaped science of synthesis in many ways. And therefore, I think it is more than appropriate to hold the symposium in his honor at this very special point in time when we celebrate 20 years of science of synthesis, and we'll soon have the opportunity also to celebrate Professor Trost's upcoming 80th anniversary. So let me thank you, Barry. Let me thank you, Barry, for the many years of successful service for science of synthesis. But what is more, I would like to congratulate you on behalf of the entire board on what you have accomplished during your career. You have shaped our field, and you have arguably changed the way organic synthesis is practiced today and in the future. And with this, I would like to end my brief introductory remarks. I think it's time to hand over to Professor Gary Mollender, also a highly esteemed and long-term member of the Science of Synthesis Board, who is going to chair the scientific session. So thanks again to all of you for your kind attention and for your interest in this very special event. Gary, the stage is yours.
Thank you so much, Alois, for that very kind introduction, and especially Fiona, who gave me more credit than I deserved. I can tell you, she's done the yeoman's work on all of this, but it's characteristic, I think, of TIMA, that the people, the professionals at TIMA, how much they help authors and editors put these fabulous works together. And I just want to give a shout out, not only to Fiona, but also to Karen Muirhead Hoffman, Alex Russell, Toby Reeve, and Marcus Wright, who do an amazing job of formulating these chapters that come in, sometimes very good, sometimes a bit crude, and the result is just a phenomenal contribution, I think, to our craft. So I just want to thank all of the people at TIMA who make all of this possible. And of course, I'm honored, and it's a great pleasure to be able to participate in this event, the 20th anniversary of Science of Synthesis, but also to celebrate the contributions of Professor Trost and everything he's done, not only for Science of Synthesis, but for the community at large. And I think as we listen to the speakers today, you'll see what everyone who's been in his group and in contact with him think about him as in terms of his mentoring capabilities, his science, and just everything he does for our community. So I don't want to spend too much time, talking about those types of things, but I think we got to get into the science now. And as I said, it's a great pleasure for me to be involved with this, because the people who are giving talks today are really all dear friends of mine. And the first one, Janine Cossy, is a very special friend I've known for more years than I'd like to state. Janine was born in Reims in France, where she completed her undergraduate and graduate studies at the University of Champagne-Ardenne, working for Jean-Pierre Pet in photochemistry. And I first ran into her in the Trost group when we were both postdocs there. And I think at the time, the group was probably 10% French from what I can remember, but obviously Janine had a huge presence in the group. Subsequently, she went back to France and became a director of research at the CNRS, and then was appointed to one of the most prestigious chairs in organic chemistry in France at the USPCI in Paris. And from there, her career just went ballistic. She's been a spectacular career at CNRS and USPCI. In 1996, she was awarded the CNRS Silver Medal, which is a very prestigious honor. And she was nominated the Chevalier de la Légion d'Honneur in 2018. And most recently elected to the French Academy of Sciences, which is the most prestigious honor, I think, that a scientist can have in France. I didn't know until 2 or 3 weeks ago that she's also been involved in starting several startup companies in France. So she's an entrepreneur and translating her chemistry into the community. And what I can say is that she's been a tremendous role model for young women in Europe. I think all the women that I'm familiar with in France and beyond in Europe and even in the United States really look up to her as a model. And today she's going to talk to us about strain rings and drugs, how to introduce them in molecules. Janine?
Can you hear me and see my screen? No? Oops. Can you see my screen? Can you hear me? Okay. Okay. So thank you so much, Gary, for your nice introduction, probably too much. And I would like also to thank you for the invitation, and also Alois and Fiona as well as the TIMA team for its help. I would like also to thank Barry, because I mean, Barry, you have taught me a lot of things. And before going to your group, I didn't want to spend all my life in a chemistry lab. But after my postdoc, well, I'm still in a chemistry lab. So thanks to you. Thank you so much for everything. Okay, so if we are looking, for example, at the Nadjason and Taylor classification, the most present cycles in drug on the market in 2014 and even right now, it is the benzene ring, which is represented in here. And after you have a number of heterocycle in the classification, and the cyclopropane as the 10th position. But the cyclopropane is pretty important and play a role in this kind of for the molecules, from biological molecules. And in this context, we were interested in the synthesis of this amino acid having a cyclopropane in the alpha position. In fact, these kind of structures are present in a great diversity of bioactive compounds, such as, for example, the boceprevir, which was synthesized by Merck, and it is an HDC protease inhibitor. You can recognize this structure at this position. And this kind of cyclopropyl amino acid are also included in this macrocycle, which is also an HDC protease inhibitor. And this compound, which is a neuroleptic and anxiolytic compound, was synthesized by Eli Lilly. And you can recognize this kind of structure at this position. So, I mean, we were interested in the synthesis of this kind of structure. How can we do it? Well, maybe we can have access to this cyclopropyl having an amino ester derivative from this glycolate or glycinate. And the hypothesis was that maybe we can have the access to this compound from this methylene cyclopropane. Of course, we have to control these two stereogenic centers and this one also. Probably this one will be controlled by a hydrogenation of the double bond due to the presence of this group at this position. Now, this product should be obtained from an iron-Claisen rearrangement in order to get the formation of this cyclopropane. And if we have a good control of this double bonding here for the configuration, probably we can control these two stereogenic centers. Why? Because the iron-Claisen rearrangement takes place via this 6-manganese transition state, which is represented in here, and it is a concerted mechanism. This product should be obtained from this glycolate by treatment under basic condition, and the anion should be quenched by TMSCl. Now the problem is, how can we synthesize this product? Well, maybe from this dibromocyclopropane. And if we are treating this compound by 2 equivalents of N-butyl lithium, we have the generation of this carbon ion, which can be quenched with this aldehyde in order to get the formation of this allylic alcohol. And then if we are treating this compound by the protected glycolic acid, we can get the formation of the ester. So now we are in good position to treat this compound under basic condition in order to see if we can get the formation of this methylene cyclopropane. So it's what we did. We treated this product with cash-MDS for equivalence in the presence of TMSCl at -78. So we got the formation of this product. And here we have a good control of the configuration because we have the complexation of the potassium by the oxygen of the protecting group of the alcohol. And then if we are treating this compound now, this silylenol ether by HCl, and if we are raising the temperature, we get the rearrangement to go that lead to the formation of this silyl ester. And then if you are treating this compound by TMS diazomethane, you get the formation with the formation of the ester. The iron-Claisen rearrangement is really a concerted mechanism via this 6-manganese transition state. If we have an optically active compound, normally we could get a good transfer of chirality. So we have synthesized this compound in here with an enantiomeric excess of 88%, treated this compound under the previous condition, cash-MDS, TMSCl, then HCl, and then TMS diazomethane. and we obtain the formation of the desired product with an enantiomeric excess of 87%. And in fact, we have the formation of this intermediate in the reaction media. The reaction is very general. You can have different R group in here, such as, for example, a side chain with a benzoyl group or TIPS group, or you can have, for example, an aromatic groups in here. You can have also heterocycles, such as pyridine, or you can have the this group in here on the cyclopropane that can be 2 ester group, or you can have even hydrogen. And you can see that for all these compounds, we have a good yield in between 50 to 90%. So we can have the formation of this kind of compound in here with a very good transfer of chirality, and we can control these 2 stereogenic center in here. Oops. But before, we have to reduce this compound at this position, to reduce the double bond in order to control the 3rd stereogenic center. So the thing that we did is treated this methylene cyclopropane with under hydrogen in the presence of this rhodium catalyst, and we could get the formation of this cis-cyclopropane. We obtained a very good diastereoselectivity, probably due to the presence of this group, this hydroxy group, which is protected. And due to the steric hindrance, we have the formation of this cyclopropane with the cis configuration. Now, if we are deprotecting this hydroxy group at this position by using DDQ, followed by hydrogenation by using this trap-3 catalyst, we can get the formation of the trans-cyclopropane. And here also, the diastereoselectivity is good, and due to the presence of this hydroxy group that can do a complexation of this iridium catalyst. So we could get a very good control of these 3 stereogenic centers from this glycolate. And if you are doing the deprotection of this hydroxy group, followed by Mitsunobu reaction, we will have an inversion of configuration, and we can get the formation of this amino ester having a cyclopropane at this position. Now, if we want to have the other diastereoisomer, which is represented in here, what do we have to do? Well, maybe to start from a glycinate. And if you are treating this, rearrange this glycinate according to the Ireland-Claisen rearrangement, we will have the formation of this methylene cyclopropane. And then after reduction of the double bond and deprotection, we should get the formation of the desired compound. So we have prepared this glycinate and treated this compound by LE-HMDS in the presence of TMSCl. We got the formation of this intermediate, and by raising the temperature, we have the Ireland-Claisen rearrangement, which is taking place, leading to the formation of this product in here. And after hydrolysis and esterification, we got the formation of this methylene cyclopropane. And of course, these 2 stereogenic centers are controlled with a good diastereoselectivity. As you can see, whatever the R group in here, you can get very good yield in this rearranged product. Now, we have to cleave the protecting group. So we have treated this compound by TFA, 2 equivalents, but we have only the mono deprotection. The yield is good, but for the other deprotection, we have to use TMSO triflate in the presence of 2,6-cytidine that lead to the formation of the desired compound. So we were able to obtain the formation of this cyclopropyl amino ester. But we were also interested in replacing a phenyl group by a strain ring, and particularly cyclopropane. In fact, as I said previously, you can find a lot of compounds or drugs with a phenyl ring. It is the most common group that we can meet in drugs, but there is some problems related to this phenyl group. You can have problem of toxicity, bioavailability, and solubility. And in order to avoid this kind of problems, there is one way is to replace, for example, this aromatic groups by strain ring, and such as, for example, cyclopropane, which is a good bioisoster for the phenyl group. And in fact, in addition, escaping from flat land, you can have a better chance to have a compound on the market. For example, if you consider this product in here as a baton, which is an anticoagulant product, if you are replacing the phenyl group by a cyclopropyl, you have the anticoagulant activity that is increased by 10. There is some other bioisosters of the cyclopropane, such as a cyclobutane, a cubane, an adamantane, or even this bicyclopentane. And for example, if you are replacing these aromatic groups in here, in this compound, which is a gamma secretase inhibitor, which can be used for the Alzheimer's disease, and you can get the formation of this compound by using replacing the benzyl by this bicyclopentane. In fact, you have a better activity and you can improve the passive permeability, the aqueous solubility, and the metabolic stability. So the product is much more active than this one. So for our part, we were interested in replacing the aromatic group by a cyclopropyl, a cyclobutane, or a bicyclopentane. Well, how can we do it? Well, maybe by using a cross-coupling reaction in between an allyl derivative and a cyclopropyl metal. For example, you can use a cyclopropane with a boron derivative at this position, boronic acid, boronate, trifluoroboronate. Gary has done some work with this kind of a compound. And if you are using, for example, an halide, you can have the formation of this mono-substituted cyclopentane. For example, with this boronic acid, you can use allyl, benzyl, and vinyl, but you do not have the coupling constant, the coupling reaction by using, for example, an alkyl. And in fact, you are using palladium as the catalyst. You can do also coupling reaction with NiPN. It's really the only example that you can do a coupling reaction with an alkyl, but you have to use nickel catalyst. You can use also organometallics such as the zinc derivative, but here, if you are using the palladium, there is only in the literature, the thing that is reported is only the coupling with sp2 halides. A Grignard, you can use also a benzyl by using a nickel, so you use something that is really activated. You can do also coupling reaction with copper catalyst, but it is only with primary alkyl halides. Lithium derivative, you can do also coupling reaction with iron, and here you have also one example with a primary alkyl, but you do not have anything with, for example, secondary alkyl, and it is really something that we wanted to do. So what is our goal? Our goal was to obtain substituted cyclopropyl derivative from alkyl halide, secondary and primary and secondary alkyl halides in the presence of a Grignard. We wanted something to be in a reaction that can be robust, chemoselective, easy to handle, transposable to a process, and by using a very cheap catalyst. And we wanted to have also substituted cyclopropane that we cannot observe in the literature. So, I mean, what kind of catalyst? Well, since a few years, we are working with the cobalt catalyst. So we tried to choose the cobalt catalyst in order to see if this kind of transformation was working. And after some optimization, screening and optimization, we found that if we are treating an alkyl halide, primary alkyl halide at first, in the presence of a Grignard cyclopropyl, in the presence of cobalt ACAC and TMEDA, we can get the formation of the coupling product. The reaction is general. You can have primary alkyl with, for example, this phenyl having a methoxy group in here, or you can have an alkyl with a primary alkyl with a benzoyl or a TBDS group. And here you can see that the yield are pretty good. In addition, the reaction is chemoselective. You can have, for example, an ester group, and you can see that the yield is around 56%. You can have a nitrile. The yield is not really good, 31%. But if you are increasing the steric hindrance in the alpha position of the nitrile, the yield is increased to 81%. The reaction is very chemoselective. It's not working, for example, on this aromatic having a bromide in here. So you can do some other coupling reaction. And here you can see that the yield is not too bad, 78%. Now, is the reaction working with secondary alkyl group? Well, we were using, for example, this iodopiperidine in the C4 position, and we can do under the same condition as previously, the coupling reaction with this cyclopropyl Grignard in order to get the formation of the coupling product with a yield of 96%. More challenging is to have a iodide in the C3 position because you can have an elimination. But if you are doing the coupling reaction with this piperidine, you can get the formation of the cyclopropyl piperidine with a yield of 85%. Pyridine, that's the same, the yield is good. And you can use also, for example, this iodoazethidine, and you can get the formation of the coupling product with a yield of 91%. So we were able to do this coupling reaction in order to get the formation of this substituted cyclopropane, and we can also have the formation of polysubstituted cyclopropane. Now the problem is it possible also to do the coupling reaction with a cyclobutane Grignard, and by using primary or secondary alkyl derivative in the presence of a cobalt in order to get the formation of substituted cyclobutane. Well, the reaction is working also very well. If you are using, for example, a primary alkyl halide with an aromatic group at this position, you can get the formation of the substituted cyclobutane with a yield of 80%. With an acetidine, secondary alkyl halide, you can get also the formation of this bicyclic compound, or with the pyrrolidine, you can have also the introduction of the cyclobutane. And you can see that the yields are around 60%. Now, we try to introduce this bicyclic pentane in here in order to do the formation of this compound, this acetidine, with this bicyclopentane. So we have treated this compound with this Grignard in the presence of cobaltacac and TMDA, and we never observed the formation of this compound. So what can we do? Well, maybe to switch to another catalyst. And it's what we did. We switched to the copper catalyst, and under this condition, we could get the formation of the coupling product with a yield of 57%. So now have a look at the isoquinolone. Isoquinolone are really important compounds. They have antitumoral activities, such as, for example, this compound with an aromatic group at this position, benzyluene. You have also this product, which is an antitumoral agent, and you can see that it's a polycyclic compound, or this one, which has an immunosuppressive activity with an heterocycle at this position. All these compounds are constituted by a pyridone and an aromatic group. So what can we do if we want to increase, for example, the bioactivity of this isoquinolone? Well, maybe to replace the aromatic group by a cyclobutyl compound. So we will go away from planarity, and maybe we can have an increase of the biological activity. So how can we do it? Well, we have envisaged to synthesize this cyclobutapyridone from this cyclobutenyl hydroxamate in the presence of an acetylenic compound. So what is the hypothesis? Well, if we are treating this compound by a metal in the presence of a base, probably we will have a concerted metallation deprotonation that will lead to the formation of this metallocycle. And then after complexation with the acetylenic, we will have the formation of this intermediate, which after a carbometallation will lead to the formation of the 7-Mann-Bedouin metallocycle. And then after reductive elimination and cleavage of this NO bond, we'll have the formation of the cyclobutapyridone, regeneration of the catalyst and the base. However, this kind of transformation is quite challenging, and we were aware of the challenge. This hydrogen is probably much more challenging to activate than, for example, on the aromatic groups. And here you have a Michael acceptor, so nucleophile can attack this Michael acceptor. On the other hand, you will have the formation of these very strange metal cycles. So maybe the reaction is kind of challenging. But anyway, we try to run the reaction. And we tried to run the reaction under the condition that was developed by Park in a way that was similar to a fine-use condition. So we took this cyclobutyl butenyl hydroxamate in the presence of this acetylenic, this rhodium catalyst, sodium acetate in methanol. We try also in chloroform, DMF, and DCA, and we never observe the formation of the desired product. But you know, the reaction is intramolecular and intermolecular, so it can be a little bit of a problem. So we try to say, well, okay, let's try to run the reaction in an intramolecular approach and see if, for example, this cyclobutenyl hydroxamate can be transformed to the corresponding this kind of compound by using always the same condition. So we prepare a diversity of this kind of cyclobutenyl hydroxamate, treated this compound by the rhodium catalyst in the presence of sodium acetate in methanol, and we observe the formation of the desired product. The reaction is very general. You can have different R group in here, such as a phenyl with a bromide in the para position, phenyl with a methoxy in the para position, and you have also the phenyl with a methoxy in the ortho position. Here, for these three compounds, the yields are pretty good. Here, we have to force the condition and increase the catalytic amount of the catalyst. Now, we can have also the pyridine at this position, but the pyridine has to be protected by a chloride and to force a little bit the condition in order to get the formation of the desired product. The yield is around 55%. You can have also at this position a silicium derivative or a methyl group. And here you can see that the reaction is working also very well. You can have a different size of the chain, C2 chain or C3 or C4. And here the yield are in between 50 to 70%. You can introduce also a group at this position. And for an isopropyl, you have a yield of 81%. And if you have a benzene group, you have a yield of 77%. So the reaction is working pretty well to obtain the formation of this cyclobutenyl pyridone. So, I mean, I show you that we can have access, for example, to this cyclopropyl amino ester from this cyclopropenyl. By using an Ireland-Claisen tree arrangement, we can get the formation of this methylene cyclopropane that can be reduced in order to have the formation of the desired product. And we can control 3 stereogenic centers. You can introduce also strain ring in molecules, which are important bioisoesters of aromatic groups by doing coupling reaction in between Grignard reagent in the presence of an alkyl halide, for example, and a cobalt salt, you can get the formation of the coupling product. You can introduce this bicyclopentane by using a coupling reaction in between a Grignard and an alkyl halide in the presence of a copper. And then you can obtain the formation of this bicyclic compound by using this kind of CH activation from this butenyl hydroxamate by using the rhodium catalyst. So the thing that I have now to do, because I didn't do, of course, any of these experiments, and I'm really grateful to all the group, past and present. And I'm really also grateful to Christophe Meyer for all his work and his dedication to chemistry. Christophe is a director of research at the CNRS. I would like also to thank Amandine Guérino, who is a maître de conférence at the SPCI, also for all her work. And I would like to thank the PhD students that were working on this project, Guillaume Mernouf, Claire Andersen, and Thomas Saed, for all the work also that they have done in the group. I would like to thank the SPCI, the CNRS, Divergim, and Sanofi for the financial support for the project that I have presented you. And I would like, of course, to thank the teamer for this symposium, and all of you for your kind attention. Thank you so much.
Thanks so much, Janine. That was a fabulous tour of small molecules. And we have some questions. So if you're available to answer some questions, we have some time. So Luis Mori Quiroz asked, regarding the Claisen rearrangement towards cyclopropyl derivatives you presented, have you explored the 2,3-Wittig rearrangement as a complementary approach to build two vicinal stereocenters to a cyclopropane, which is potentially a stereo-defined olefin?
No, we didn't try the Wittig rearrangement. We try only to this Ireland-Claisen rearrangement.
Okay. So I'm trying to keep track of these. James Fordham asks, is it possible to extend your cobalt catalyzed Kumada coupling to alkyl chlorides, bromides, or pseudo halides?
Okay, well, we try with bromide and it's working, but the yield is not as good as with iodide. And chloride, I'm not sure we tried because, I mean, the bromide was giving low yield than the iodide. And you have much more, with the bromide, you have much more elimination compounds than with the iodide.
Okay. So Michael Harmada, another Trosty, do the puridones open thermally?
Well, we were afraid of this, but yeah, if you are eating the compounds, it's open to give the two double bonds at the top of the cyclobutane, and then you can do cycloaddition if you want with the intermediates.
Okay, there's a question about the practicality of this, and is the industrial manufacture of these small ring molecules economically viable, or are they applicable for high value, low volume products?
Well, I mean, we were working on this kind of project with Sanofi, and Sanofi is ready to use this kind of methods in order to introduce this cyclopropane in their molecules. After, I mean, if you are working on tons, I don't know.
Yeah. I guess, yeah, if they want it badly enough, I guess they'll make it economical for you. So
yeah,
maybe a couple more questions and then we should probably go on. Is it possible to extend the cobalt catalyzed Kumada coupling to alkyl chlorides? Oh, we already answered that one, didn't we?
yeah.
Okay. And between primary and secondary iodides, which one is better substrate for coupling? And can the other halides be useful for coupling reactions?
I mean, both of them for the alkyl secondary and primary alkyne, they are working pretty well. I mean, it's not more, you have no more elimination, for example, with the secondary halide. These two are working pretty well.
Okay. Another question.
For pseudo, we didn't try with the cobalt, but it's working very well with the, for example, mesylate and tosylate is working very well, but you have to switch catalyst, and we were using the copper instead of the cobalt.
Okay. Let me see. So well, there's lots of questions. How stable is a cyclobutane ring in the presence of rhodium metal? Rhodium doesn't insert between the carbon-carbon bond of the ring?
No.
Okay.
I mean, as you've seen, well, the yield are pretty good under these conditions. Okay. The only thing that we were also worried, I missed to say, but it was to heat this compound and that they can be degraded. But after getting these compounds, we did the heating of the cyclobutene. And as I say, we had the bismethylene that can be involved in, for example, these other reactions.
And someone's asking about the stability of the cobalt in the air. Can you do these reactions in the air, or you have to, it's all under nitrogen or argon, or?
Well, I think we never tried to do under air. We did the reaction under nitrogen.
Okay. And maybe one last question, was the mechanism of the cobalt catalyzed coupling reaction investigated?
Yes, we tried to see if we could have a radical reaction. And well, we synthesize. I don't know if I can share again the screen. Yes. Let me see. And we found that it was a radical reaction. We prepare this kind of piperidine with the iodide in the presence of this double bond in here, and treated this compound with this Grignard in the presence of the cobalt acetate. If we have a radical, we should get the formation of this compound. And in fact, the thing that we obtain is the formation of the bicyclic compound with the cyclopropane at this position.
Okay. Well, with that, I think we have to move on. So I will thank Janine again for a spectacular seminar, and thanks for participating.
Thank you, Gary.
No problem. So we're going to stay within Europe and hear something from Nuno Maulide. And what should I say about Nuno? So Nuno was born in Lisbon, and he graduated from Instituto Superior Técnico with a bachelor's degree and then a Master of Science at the École Polytechnique, and then received his PhD from the Université Catholique de Louvain in 2007. And he came to the United States to postdoc with Professor Trost, and then became a research group leader at the Max Planck Institute in Mulheim. And since 2013 is a full professor and chair of organic synthesis at the University of Vienna. So Nuno is probably the most versatile chemist and maybe person I know. So obviously multilingual. He could have had a career as a concert pianist. I can vouch for the fact that he could have won Dancing with the Stars competition. But fortunately for us, he stuck with chemistry. And actually last year, the year before, he was Scientist of the Year in Austria and the youngest corresponding member of the Austrian Academy of Sciences. And just this year was awarded the Tetrahedron Young Investigator Award and has a spectacular program going in Vienna. And he hangs out with Schwarzenegger at expensive Viennese restaurants too. So Nuno, why don't you take it over?
Thank you very much, Gary. Once again, far too kind in your introduction. It's really my pleasure and honor to be here among this distinguished lineup of speakers and to have the opportunity to tell you something about the work we have been doing. Also, of course, in honor of Science of Synthesis and in honor of Barry Trost. So in today's seminar, I want to tell you a couple of stories, some small vignettes about our own research, a short total synthesis story to begin, and then we go into some amide activation before finishing with iodine chemistry. You will see in every one of these topics, there will be an introduction with a picture. There's plenty of pictures in my presentation. This picture here is of the main building of the University of Vienna, where you can actually see in the distance the twin towers of Vienna, the votive church. And in introducing total synthesis, I put a picture of a typical organic chemistry 1 classroom at the University of Vienna. You can see how students take their teaching very seriously. Of course, this is actually a picture of the ball season in Vienna, which I guess is not really COVID compliant. But in any case, it dawns on me that while working on this type of total synthesis and trying to make the most of abundant resources for organic synthesis, one has to go back to the good old days spent at Stanford. And it was really a great time for me. I was there between 2007, 2008. You can see how happy I was at the desk in the lab. You can also see how much we enjoyed ourselves in the lab, especially when wearing particularly fancy clothes. And one thing that was always impressed on me during this time at Stanford by Barry himself was the need to be efficient with the use of resources and not be wasteful. And our rotovaps at Stanford, I think, very nicely illustrated that, showing that you don't really need to have the fanciest of equipment to be able to do world-class science. I guess if my coworkers saw these, they might actually come to complain to my office. And that's more or less the same vein into all these story of total synthesis begins for us, because we were very interested in the notion that this compound here, oleanolic acid, is something that is virtually dirt cheap. You can buy it for less than $1 a gram, extremely abundant. You probably had some of it today if you had anything that contains olive oil, or if you ate olives at lunch or dinner. And oleanolic acid is such an abundant and useful compound, but at the same time is pretty much a grease ball with only one carboxylic acid and one alcohol as functional groups. So not a lot of functionality and not a lot of solubility and bioavailability. Now contrast this with the work that P450 monooxygenases do in converting oleanolic acids through a series of CH oxidations, and I've marked the CH bonds in green here for you, into a molecule called protobasic acid, which is an extremely potent compound from a biological point of view, way more bioavailable and with much improved solubility. Actually, an extremely strained molecule. We just heard Janine speaking about strain. All these OHs and methyl groups have 1,3-diaxial strain among themselves. And one can only imagine using the power of CH oxidation and CH hydroxylation. That's actually pretty much what you need in this case, right? If you're only able to do 3 CH hydroxylations at the positions marked here in green, voila, you would have protobasic acid, which, by the way, as you might expect, can't be bought by any supplier. Now, some of the most famous organic chemists of our day have tried extensively to do CH oxidations at oleanolic acid and have faced multiple problems. Most of those problems being related to the fact that no way, Jose, will you be able to oxidize the axial CHs when you have these methyl groups all positioned there like trees standing on your way. Plus, the positions marked in green are not even necessarily the intrinsically most activated positions for abstraction by a conventional homogeneous catalyst. And so one realizes relatively quickly that the way to do this is to perhaps recognize that there is a proximity aspect between the one hydroxy group present in oleanolic acid and the C23 carbon-hydrogen bond as a potential handle point for starting oxidations. Now, the issue is you might be able to do so and place one OH group, but what about the other ones? And we thought about using this hydroxyl group as a relay. Why don't we use that to introduce the first hydroxylation center at C23, and then use the newly formed hydroxy group to introduce the additional OH at position C6, probably at first in an equatorial sense, and then attempt to do some kind of diversification to lead us to the final products. And what I'm going to show you in a very summarized way is what we have done as a method to achieve a so-called relay sequential oxidation of oleanolic acid. We do it in a sequence of reactions which have been optimized, at least the first steps, on a decagram scale. So we have optimized a sequence which converts oleanolic acid into this molecule here by sequential bromolactonization, which protects the double bond and the carboxylic acid, followed by oxidation with trichlorocyanuric acid and formation of an oxime with hydroxylamine to lead you to this oxime here, where the bromolactone shields the isolated double bond of oleanolic acid. At this point, we can take advantage of the great chemistry developed by, among others, Melanie Sanford, to do CH acetoxylation, indeed taking place preferentially at C23 on this side of the molecule, giving you this acetate with a DR of 3:1. The 56% is already the isolated yield for the desired product. We can then, at this stage, unleash the ketone, releasing the oxime by a hydrolysis with K-carbon methanol, followed by copper sulfate. And at this point, we thought, well, let's start planning how to install the second OH group at this green position here by directing from this newly installed hydroxyl. And we thought immediately of using radical processes that would mediate 1,5 hydrogen atom abstraction. You can count 1, 2, 3, 4, 5 into this position. Now, what we saw when we tried to form an oxygen-centered radical was that rather than do 1,5 hydrogen atom transfer, what actually happened was fragmentation with release of formaldehyde and the stabilized alpha carbonyl radical. So at this point, we thought it might be necessary to somehow mask this ketone. And once we did so by protection with ethylene glycol, then we were able to do the 1,5 hydrogen atom transfer, which finalizes with ether formation, giving you this cyclic ether in 53% yield over the 2 steps. Now, at this point, we knew after deprotecting the acetal by X-ray that we had done the required CH oxidation at the desired position. And we were now faced with the need to convert an ether into a diol. Not that straightforward of a transformation, but of course, we could rely on the notion that C23 could be oxidized by high-valent ruthenium to give you the lactone out of the ether. And we felt that with this lactone, we should be in a good position to continue our manipulations. So at this stage, we found out serendipitously that reduction with excess lithium aluminum hydride does not completely reduce everything in a molecule. It reduces the ketone to an alcohol. It reduces the lactone to a diol, but it somehow stops at the lactol stage when it comes to this bromolactone. This is something that is a purely empirical observation, but actually it allows us to capitalize on that by doing a zinc reductive cleavage to regenerate the olefin and allowing us to stop at the aldehyde oxidation state rather than be faced with an alcohol. We could at this stage mask these 2 alcohols into an acetonide with PPTS and acetone, and then reoxidize everything in order to prepare the conversion of this equatorial C6 into the required axial orientation, while at the same time regaining the carboxylic acid, which is characteristic of this family of natural products. And so the end game is relatively straightforward. We deprotect the acetonide and reduce the C6 ketone with lithium borohydride to install this very delicate C6 axial OH. In the case where there is no substituent at C2, this molecule is a natural product called uncargenine C. In the case we have previously introduced hydroxylated functionality at C2 by means of lead tetraacetate, the whole sequence leads to a product delivering protobasic acid with the all axial arrangement of OH groups. Now, one may criticize there are, of course, redox economy aspects that one might improve in this sequence, but we are very comfortable with it because it can be reasonably scaled and it leads to the discovery of additional analogs of these natural products, which we are very interested in studying the biology thereof. So these are the heroes that carried out the work. We published the work earlier this year in Chem. Martin Berger, who is now doing a postdoc with Paulo Melchiorre, and Christian Knittel-Frank, PhD student in our group. We now go back to methodology, and part 2 of this talk focuses on amide activation. You see here a picture of the beautiful palace Schönbrunn, the summer palace of the emperor and empress in Vienna, in the outskirts of the imperial city back in the day. You can see that the picture must have been taken during some kind of a lockdown moment because you rarely will see Schönbrunn's main courtyard this empty. And again, when searching for projects and ideas to take on new projects, one really has to say that it's your previous mentors that guide you in the way you end up eventually developing your own research program. And I'm very, very grateful to Barry for all that I've learned in his lab. Barry came to Vienna to visit us, more or less by surprise. I guess it was during a Science of Synthesis board meeting in Vienna that there was a couple of hours left for Barry to visit us. And of course, I had to take him to probably an institution where Barry himself would have liked to work, the University of Vienna Institute of Organic Chemistry. In any case, you didn't get a job at this university yet, Barry, but we were very happy to see you sitting in our main courtyard in our Universität Wien chairs. And it was really a pleasure to see you around when you came to Vienna. Now, the inspiration for this work comes from something we teach our undergraduate students in very basic organic chemistry courses, namely that electrophilicity in carbonyl compounds increases when you progress in the series from carboxylic acids and amides all the way to aldehydes and ketones, and ending with acid chlorides and anhydrides. This is something that is well ingrained in the minds of most of our undergrads. But something we don't necessarily tell our undergrads as strongly is the notion that something else increases in the opposite direction, and that is the nucleophilicity of the carbonyl oxygen. That one is highest on amides and, of course, on carboxylates. That's a property that Léon Gauzet, among others, but I think he's really the pioneer, has championed since the 70s and early 80s in developing a chemistry where tertiary amides, such as this one, are activated with triflucan hydride, a strong electrophile, and the pyridine type base to form as intermediate a keteneminium ion. Now, Gauzet showed extensively that these species, very unstable and very fleeting intermediates, engage electron-rich double bonds to form, by a formal 2+2 cycloaddition, cyclobutyl-iminium ions, and after hydrolysis, cyclobutanone as products. Charette, in probably the most highly cited paper of the Canadian Journal of Chemistry, has shown more in detail what's going on in this process. You have a first activation of the carbonyl oxygen by triflucan hydride. This gives you an iminium triflate, which then gets activated further by the pyridine base, losing the elements of triflic acid and generating the keteneminium. You probably never see a keteneminium ion in solution under these conditions because it tends to immediately be intercepted by the pyridine base that you employed in this type of process. And this is indeed the resting state that one typically sees in NMR, as Charette beautifully showed in his pioneering work. Our own group has been very active in this area. We published a perspective in JOC 2016, and we've also reported a review on amide activation 2 years later in ChemSoc Rev. I would direct you to those publications if you're interested in some of the earlier work we have done, because this is a tribute to Barry. I think it's more useful to show some of the more recent and more exciting developments. And one of the things we found very exciting, heavily borrowing from the chemistry of Léon Gauzet himself, published the year I was born, 1979, Gauzet showed that one can actually intercept keteneminium by other types of nucleophiles, such as, for example, N-oxide. And we were very interested in this concept because we felt that interception by pyridine N-oxide would lead you to a species with a transient intermediate where something must have happened to the polarity of this center, since this species now should behave as an electrophile, whereas the original amide, of course, always has a delta minus in the alpha carbon by virtue of a potential enolate formation. And so we felt this would be a very interesting blueprint to develop alpha functionalizations of amides, where the alpha functionalizing element would not be an electrophilic species, but rather a nucleophile that adds to this position, forms a CO double bond, and kicks out pyridine as a leaving group. And as simple and as naive as this idea might appear to the audience, and I hope it at least comes across as simple, it does have a long mileage because you can do a lot of things with this very simple principle, which I guess even my undergrads, organic chemistry too, should be able to understand. That's because once you do this, you are able to take a simple N-benzyl, so this would be a N-benzyl amide, a protected amide. The N-benzyl group itself is able to engage the intermediate I've shown you in the previous slide, this species here, in a Friedel-Crafts-like process to give you lactams. And we've seen the beautiful chemistry of Janine Cossy's group in forming pyridones and fused quinolones. And this would be a kind of a different entry to form quinolones by this CC bond forming event highlighted here in blue. We reported this also a couple of years ago. Same year, we reported that one can actually add oxygen-based nucleophiles. And if those are themselves oxidants, for example, pyridine N-oxide itself, then it's possible to rebound after the nucleophilic attack and end up with an alpha keto amide. This is probably the only method that allows one very smoothly to prepare an alpha keto amide from the corresponding amide in the presence of a lot of different functional groups. But if you think about what one would like to put alpha to a carbonyl, that is intrinsically difficult to do because of polarity aspects. There is one element which certainly hates being the electrophilic partner, right? Because it's the most electronegative element in the periodic table. And I'm of course referring to fluorine. How cool it would be to do alpha fluorination, not having to rely on the select fluors of this world, but rather on fluoride in its native form. And I don't have to explain why this would be valuable also from a medicinal chemistry perspective, because fluoride is a very common bioisosphere for both hydrogen and oxygen. And one thing that is particularly appreciated in medchem is the notion that the carbon-fluorine bond is much more stable than the carbon-hydrogen bond. Therefore, it's not surprising that more than 20% of newly approved drugs typically contain at least one fluorine atom. If you count the number of things that have CF3 groups, then you actually have 3 for the price of 1. A very common strategy to increase stability towards metabolic oxidation, and typically used, for example, in the case of amines, to increase bioavailability while slightly reducing activity. More on this in a couple of slides. There is a hidden side to fluorine chemistry that I was at least not entirely aware of, and that's the fact that when you go to PET and use F18 as the radioisotope, you are faced with a big issue, and that is that using reagents that are based on F+ equivalents is not so great, since what one gets from the synchrotron is actually potassium fluoride labeled with F18. And then the clock is kind of ticking because this thing has a half-life of 110 minutes, and one wants to use it as a PET tracer before its decay is gone. And so it would be way better to be able to use 18F- than 18F+. And the method I'm going to show you kind of offers a window to look into that, because we have done exactly what I've been showing you until now, namely an activation with a pyridine base. I can't really say why sometimes 2-fluoropyridine is better than 2-iodopyridine. Sometimes it's 2-methoxypyridine, sometimes it's 2-bromopyridine. There probably is going to be a question or two in the chat about that. It is pretty much empirical. There's no big rationale a priori to say, for this method, use this pyridine, for that method, use that pyridine. It's pretty much trial and error. In combination with one equivalent of tryptophan hydride, 15 minutes, that leads you to this ketiniminium kind of biased equilibrium, to which you can add lutidine and oxide. We found out that in this case, lutidine and oxide is better than pyridine and oxide. In 5 minutes, the unpoling event is kind of complete. And then we just have to add a fluoride source, 3 equivalents, room temperature, 23 degrees. We chose to use TBAT, because that's something you can get anhydrous and therefore leads to more reproducible results. But I'll show you in just a couple of seconds that you can also use other fluoride sources. What's important to point out here is that indeed we have a very broad scope, and something which I find amazing in amide activation done under these conditions is its functional group orthogonality. Look at the substrate scope here, and you'll find substrates where the amide is sharing the same molecule with an ester, a ketone, or a nitrile. And you see that the only action takes place in the alpha position of the amide, which is something that I guess would be virtually impossible if you're relying on inulate chemistry, because of course, if you wanted to do alpha deprotonation, then the ester or the ketone, or even perhaps the nitrile, would be a little bit more CH acidic than the amide and will get deprotonated first. But of course, this chemistry doesn't rely on alpha CH acidity, does it? It relies exclusively on carbonyl oxygen basicity. And in that competition, ladies and gentlemen, the amide oxygen always wins. Which is why you can have this derivative of cholic acid, where you have not 1, not 2, but 3 ketone carbonyls, and all of them are oblivious to the chemistry that happens up there at the end, where the amide is located. As I mentioned to you, fluoride sources were something that we wanted to explore. And as you can see here, if you use TBAF, you can also get decent yields. They're actually a little bit lower than the case of TBAT. In this case, I think we get 90% yields with TBAT. We go to 79% with TBAF. But we can also use TBAF, and after 15 minutes quench the reaction, the yield is almost the same. You get a 10% decrease. And if you use potassium fluoride, which is of course completely insoluble in DCM, and combine that with cryptofix 222, namely cryptand that pretty much sequesters the potassium and allows you to solubilize to some extent potassium fluoride, then you're actually able, even with 15 minutes reaction time, to end up with a decent 60% yield. And why is this important? Because this indeed opens the window for ladies such as Véronique Gouverneur, one of the world experts on F18 labeling, to potentially be able to explore this chemistry, because now we are doing it under conditions that suddenly become relevant for F18 labeling. And this is something we are very excited about, extending the scope of this methodology to really be able to use it in contexts where it might be relevant to patients in the clinic, right? Because PET is something that directly impacts patients. But to be honest with you, I'm but a poor, naive organic chemist who likes to have fun with molecules. And to me, it's particularly fun to look at a molecule like this, piperylene, a blockbuster fungicide, or to look at this one, fentanyl, a compound typically found around train stations worldwide, or citalopram, as I always joke, a compound you could give to PhD students the last year of their thesis, probably sorely needed. And all these compounds have very different structures, but we all know by now enough chemistry to be able to imagine making the fluorinated analogs shown here, specifically at the positions shown there. I'm going to show you how we did that for citalopram. We used the intermediate in the commercial synthesis of citalopram. This compound is commercially available. You can get it by the bucket. And you can deprotonate here and do a Michael addition with acrylamide, followed by alpha fluorination of the amide, which gives us a mixture of diastereomers. We can separate it. And then reduce the amide, again, chemoselectively without touching the nitrile, to give fluorocytalopram. Why is this relevant, you may ask? A, because this molecule is not known. B, it's not even covered by the Eli Lilly patents. So one could actually now start having fun and looking at all blockbuster drugs and figuring out, can I put a fluorine somewhere using this chemistry in that molecule by having an amide precursor? And then can I go and knock on the doors of medical doctors, such as Harald Sitte at the Medical University of Vienna, and ask them to do functional assays with these compounds? I think this is very valuable because this is a symposium about chemistry and medchem, and there is this notion that organic chemists are always at the service of biologists and medical doctors, right? They are the ones who come up with ideas, and then we have to execute those molecules. We are the ones who can think in molecular and atomic terms. We are the ones who should be driving new ideas in the medicinal chemistry field. Because precisely when you have chemistry that enables you to do things that were not possible before, you are able to dream beyond what has been done until now. And you can see in this functional assay that, of course, because you place the fluorine in that position, you lose a little bit of activity between citalopram and F-citalopram. The amine is, of course, much less basic now that you have a fluorine pulling electron density from there. You can see in this docking pose that we believe actually the fluorine allows you to gain one additional interaction with the tyrosine residue. That's why you don't lose that much of activity, because usually the loss would be expected to be much higher. What makes this interesting from a pharmacological point of view is the potential for much changed pharmacokinetics, because of course you have blocked by fluorination here what probably is one of the hottest points for metabolic oxidation. What else have we done with this chemistry? We're also able to add enolates as nucleophiles, and through that achieve a very interesting approach to 1,4-dicarbonyl synthesis, which we have also reported a couple of years ago. I don't have time to go into that now. What I'd like to tell you in the final part of the talk, I'm checking the time to make sure I'm not overflowing, is how we got interested in iodine chemistry, precisely departing from this notion of umpolung. I'm showing here a famous fellow that lived a couple of centuries ago in this very city, in Vienna. Barry, I think you're kind of a Mozart of chemistry, so I think for this picture, I don't need to put one of you. And iodine is really a great element when it comes to attempting to overcome natural polarity of carbonyl functionality. That's because, of course, intrinsic umpolung is achieved by expedients such as Thaioketal, the beautiful Seebach-Corey original coining of the term umpolung, but also by catalytic methods. This is, of course, the cyanohydrine variant, but NHC catalysis has been exceptionally productive at achieving this type of umpolung. We were more interested in a kind of redox umpolung, which is also kind of well established for iodine species, namely that you would form again, an inolonium type of intermediate, but now rather than having a pyridine attached to the oxygen, you would have an iodophenyl moiety. It's well known that these intermediates are then displaced by nucleophiles to give, in a similar vein as what I've shown you before, alpha functionalized carbonyl compounds ejecting iodobenzene. This is the redox event, right? Where iodine goes from +3 to +1. Now, we felt, because we love rearrangements, even when we can't spell them, right? There's an E missing here. Apologize for that. We love rearrangements. And we figured out that if we were able to leverage this type of inolonium formation and think about it as the synton for an alpha carbonyl cation, then one might actually imagine some kind of rearrangement that would bring this carbocation away from the position that it so dreads, namely next to an electron withdrawing group, and by nucleophilic interception, eventually lead us to a prospect of distal functionalization or some kind of reorganization of the system. And in our previous work, that's this paper here, 2019 Angewandte, we show that one can do that by using these kinds of homobenzyl ketones that are, through by virtue of the silyl enol ether, converted into the iodine 3 intermediate, which triggers formation of a phenonium cation that gets ring opened the other way around, of course, on the least hindered position, by, in this case, methylated the counter ion, to give us this kind of beta-methyloxy alpha aryl ketones, kind of a blueprint for alpha arylation by carbon-carbon bond activation, since we're effectively activating the carbon-carbon bond that's closest to the phenol ring. And when you think about progressing from this point, you see an aryl and you think, well, let's replace the aryl with a double bond, right? And one should be able to reach something similar, namely cyclopropane as a product. We were expecting that this would give us something like that, and that interception by methylate would then lead us to the methylated methyloxy cyclopropane. We did get that as a major component, but I'm very grateful to my coworkers for always being super careful and figuring out that there was a bit, less than 10%, of another compound, namely a cyclobutane. And I have to say, there's no good rationale why you should get a cyclobutane in this process, unless the intermediate is not exactly what we think it is. And that was something we could discern by using isotope labeling experiments. Namely, by placing a C13 at this terminus, we saw that even the cyclopropane product did not have the label where we hoped it would be. That was only half of the story. The other half of the label was inside the ring. Same thing happens with deuteration. The ratio is not perfectly 1-to-1, probably because of kinetic isotope effects. But you see it here. This really suggests that one might be dealing with some kind of non-classical carbocation, that this intermediate here is not really the way I'm drawing it, but rather a non-classical carbocationic species. In any case, we went for a substrate scope. I'm not going to bore you with the details. We even tried to correlate this somehow with Hammett plots and Hammett values for the substituents on the aryl ring. I think the most important thing is to show that it's possible to use quite a few variations, especially in position number 1, and you lose this color coding here. But you can also change quite a bit things in positions 2 and 3. Of course, when you make them too different, then you generate stereogenic centers which no longer are controlled in any way. So we get a 1-to-1 DR, but we can have a gem dimethyl, and then we end up with a tertiary alcohol, even in a pretty high yield. Now, when you think about non-classical carbocations, I don't know about you, but I immediately remember the huge debate that I could only read on the literature. Thank God I didn't have to witness those fights live in conferences between Saul Winstein and H.C. Brown. But in any case, very exciting developments, and everything that is named non-classical to me reminds me of one classical system. Ben List just published a beautiful paper on using organocatalysis to control non-classical carbocations on a similar system. I guess you know I'm talking about norbornanes. And norbornanes are really the quintessential non-classical carbocation pictures that one has in one's mind. We thought, let's use a norborne ketone, make the silyl enol ether, generate the inolonium, and then let's see whether this thing really is capable of non-classical behavior. Because if it is, then you all know what's going to happen next. namely that one's going to form a non-classical stabilized true norbornyl cation. And I don't know what's going to happen, but I can imagine that this might actually be able to just lose H+ and become a Nor tricycline. And that's indeed what happens. The yields are not always perfect, but we are able to get decent amounts of these kind of cyclopropanated products, right? We form a cyclopropane by using this type of oxidative carbocation generation. Quoted here a couple of the key references for this type of chemistry. Where I think it's very important to notice is that we don't have any, and we made this compound to try to identify it by NMR, to have an authentic sample. We don't see any of compound 32. So there is absolutely no alpha beta saturated ketone, which to me tells me this is not a naked carbocation, because if it were, elimination would have been for sure a very direct pathway. Same thing with these rearranged species, which we would expect if you had a classical carbocationic rearrangement of the norbornane skeleton. We don't have any of that. We just get the cyclopropanated material. And at this point, when you look at this compound, number one here, in most of these cases, is an aromatic. But who's stopping number one from being a nitrogen? But if that's a nitrogen, then we're talking about an amide starting material. And we already learned a couple of slides ago how we in our lab have been doing umpolung of amides, right? Trifluic anhydride, pyridine and oxide. We can think about similar aspects and eventually hope for formation of a stabilized true norbornyl cation, which might also be able to cyclize. And indeed, this is the case. We do see formation of the byproduct of elimination, but you know why? Because in this chemistry, we have non-negligible amounts of bases floating around, right? So the iodine chemistry is very advantageous because it has no strongly basic species. Here we do have 2-iodopyridine and even pyridine itself once the enolonium is formed. And so it's natural that with those bases floating around, we do get a little bit more of elimination, but still we have very decent yields of the amide products. So I think this is very interesting because it allows us to come full circle and understand that we now have two different systems to do this type of umpolung, a generation of carbocations, which I think hold a lot of exciting promise for future development. Okay, that's all I had to tell you for today. I've shown in the beginning our ideas on relay CH oxidation. I think what's really cool here is how you can take something which is abundant, you can buy hundreds of grams very easily, and convert it through a relay of oxidations into a very valuable material from a biological point of view, but which of course you can only access in minor amounts from natural sources. So now we have a way to get into this compound. This is what Martin Berger, a very talented designer, drew as a, I think, very cool prospect of what one does. Place a couple of oxygens, right? Hanging from some carbon atoms in order to get the desired modification. I then showed you about our forays into amide umpolung, again, very inspired by Leon Gauzet's pioneering work, and how this leads us to alpha functionalized amides or even the products of mild oxidation. And then this final portion of my talk, where I really went into the iodine, the value of iodine chemistry, in allowing us to do these under conditions which are a little bit nicer in that they don't have basic components floating around, and how this actually leads us to discovering some interesting non-classical, at least in behavior, intermediates that one might be able to leverage for other types of chemistry. Now, I cannot finish without acknowledging the funding agents. We are very, very grateful to these agencies for generous support of our research, especially the ERC. Gary mentioned I'm from Europe, like Janine. Without the European Union, without the European Research Council, I would not be here. And I would certainly not have any chance of presenting you our work, because we just would not have been able to do it, right? So the ERC is probably the best thing that the European Union ever did for research. And I'm a strong supporter of the European Union. I think we are always stronger together than we would be separated. One thing that I'm very interested in nowadays is reaching out to the broader public. I think we chemists owe it to the public at large to remind them of how their lives would be back to the Stone Age if there was no chemistry and no chemistry research, and dispel this notion that chemicals are bad. How can we, as a discipline, allow the #1 tool of our discipline, namely a chemical, to acquire a negative connotation in everyday language? Makes no sense to me. And so we have published earlier this year a book with Tanja Traxler called Die Chemie stimmt, The Chemistry is Right, a book about general chemistry, general explanations of chemistry. Please, if you speak German, buy this for your family, offer them something chemical for Christmas. And if you don't speak German, buy the book too. Another thing that we are very interested in is connecting to the younger sides of our population. And because of the corona pandemic, together with the Association of Chemical Industries in Austria, we have developed a video game which you can actually all play for free at this URL, blaster.dchemie.at. Virus Blaster allows you to play with up to 3 characters. And you see them here. The first character is Thomas Morgenstern, a very famous Olympic gold medalist in skiing. So you can imagine kind of a superstar in the Austrian landscape. The middle one is Marie Curie, none other than Madame Curie. And the third one you already saw, it's myself. So I guess I'm ecstatic at the prospect of having become a character of a video game. You see me here fighting against the bad guys and cleaning up some viral loads. Play the game, have some fun online with it. It's all for a good cause. And of course, to finish, these are the people who do the work. I'm very grateful to them. You also see the names showing you that these are a very diverse group of people. Of course, this is not the group picture. My group is maybe a third of this. This is actually the party we had last year, pre-corona, for celebrating our 10th anniversary of the research group. And we invited all the alumni, and as many as possible came back to Vienna. We are very grateful to having had the possibility to work with this amazing group of people, to currently work with this remarkable group of co-workers. And again, I thank all of you for listening. I thank Tima for the kind invitation. I think the opportunity to be among these panelists is really appreciative of my respect for Barry. Barry, one picture to finish. I think even when you have 2 Nunos around you, they still don't really match the brilliance of one Barry Trost. Thank you very much, everyone, and I'm happy to take any questions.
Beautiful, beautiful talk, Nuno. Thanks so much. It's strange not to have standing ovations, you know, when speakers give talks, but we have time, I think, for just one question. And there's a question about from Christine Le. For the Umpalong alpha fluorination chemistry of amides, are asymmetric variants possible? She's wondering about the alpha proton might be rendered too acidic.
Absolutely.
After fluorination.
That's something we're working currently on. We've tried a bit with chiral auxiliaries, some kind of chiral amide. Sorry, Barry, I know Barry doesn't like chiral auxiliaries much. That hasn't been particularly successful. We're trying to explore alternative variants, like using a chiral pyridine oxide or other strategies, and those seem to have a little bit more promise. So that's something we're very hot in pursuit of.
Maybe one more. So there's a question from Rob Bream about, does a fluorination chemistry work in solvents other than dichloromethane, which is a likely barrier of dosing in patients?
Wow, that's a pretty good question. I would imagine acetonitrile might also have a chance. I don't think we have tried much other than DCA and DCE. I guess both of them are equally bad. So I've had this question a couple of times in industry contexts, and I think acetonitrile is probably our best bet to run away from chlorinated salt.
Okay. Thanks so much, Nuno. We'll have to stop there. And by the magic of the internet, we're going to cross the ocean. And Mark Lautens in Canada is going to be our next speaker. So Mark is from Canada. He received his bachelor's degree at Guelph and then joined Barry's group at Wisconsin-Madison for his PhD and finished off in the Dave Evans finishing school for assistant professors before joining Toronto, where he is currently AstraZeneca Professor of Organic Synthesis. Mark has had a distinguished career. I mean, the number of methods, beautiful methods that he has developed in domino Heck anion capture chemistry, CH activation, multi-component reactions, could fill many textbooks. And for this, he is an officer of the Order of Canada and a fellow of the Royal Society of Canada. And just next year, I think this is public now and has been announced, he's the A.C. Cope Scholar and H.C. Brown Award winner from the ACS for 2021. He's going to talk to us today about the wonderful world of oxindoles. Mark?
Okay, Gary, thank you very much. It's a real pleasure to be here, everyone, and I thank you for attending. Of course, I realize we're here to both celebrate Science of Synthesis and Barry Trost, and so I thought I should begin by a little bit of each of those. If I can only get the, there we go. So this is, I met Barry Trost 40 years ago. I think I was 4 years old. No, a little older than that. 40 years ago, I attended a conference that he spoke at. I visited Wisconsin and I joined his group in 1981. This is a picture of him at around that time. And when I joined the group, I realized that if I knew half as much as some of the people in that group, I would have a very successful career. And here's just 3 of the people who I had the great honor and pleasure to meet. Gary and Dennis were just leaving for their academic jobs, and Janine was going to be around for a while, and I got to know her maybe a little better than the others, but I've admired all 3 of them, and as Gary implied, the Trost labs were amazing. There were 35 people, 20 postdocs, and 15 grad students. This was the work that I did in the Trost group, so I say it because it's going to be relevant to what I tell you about today. The first project I had, and I must tell you, Barry was way ahead of his time. The project that he gave me, I just wasn't smart enough to make work. It was allylic CH activation based on a fundamental paper by John Osborne. And although I couldn't succeed at that, I did manage to succeed at finding a new catalyst for allylic alkylation. That was molybdenum, which showed unusual regioselectivity. And then just towards the very end of my PhD, I discovered this enine cyclization. The discovery was actually accidental. I tried the alkylation and I got the product, and then we figured out that if oxygen was around, maybe the palladium had oxidized. It was actually palladium-2, and so I tried it with palladium-2. Indeed, that worked just fine. So now fast forward about 15 years, Barry reached out to me as one of the editorial board members of Science of Synthesis and asked me if I would agree to be volume editor for volume 1. I immediately said yes, not thinking too much. That was probably a mistake. I should have thought a lot more. And especially because it was volume 1, we were learning all the rules of how to create Science of Synthesis, and it was especially difficult with volume 1, which was full of transition metals. And since it's a sort of a product-based, but metals tend to not be the product, it was a little bit challenging. But Barry really helped a lot with a few intransigent authors to give them a little push from somebody who they tended to listen to. In terms of listing, you know, a few people have texted me, tweeted me saying, are you going to have any funny stories about Barry? No, I don't think I'll have any funny stories, but I will have one little piece of advice he gave me. In the days when I was a grad student, there were hardly any computers. So you wrote out your thesis by hand and then paid someone to type it. Computers were just coming into being. And I handed him my thesis and he wrote back on it after reading it. Less verbiage. Verbiage equals garbage. So maybe my lecture should be over now because that's really all I have to say. But what I will say I took away from it was it's important to try to get to the point. So let me get to the point and tell you about today's research. So we talked a little bit about efficiency. We heard that from Nuno. If you think about efficiency, you can think about it in different ways. One way is to use an isomerization. No wasted atoms. All the atoms of the starting material appear in the product. Another way, what about if you can combine multiple reactions? What about if you can mimic nature and start to put all the reagents and catalysts together? So first, work with some beautiful work from Antonio Echevarren. Second, some beautiful work from Matthias Beller. And then third, what about if you start to access bonds that you normally can't react? And CH bonds were already mentioned earlier in some of the other talks. And we started on this in 1997 and have really kept on with it ever since. So how does this fit into our work? Well, let's take each of those topics in turn, and I'll give you a very fast tour of some of the things that we've done. So back in 2001, John Hartwig reported this paper which was very interesting. It was a mechanistic paper that looked at oxidative addition and the reverse reaction, reductive elimination. And what he showed was oxidative addition, which is normally the favored pathway, can be reversed in the presence of the right sort of ligand with the right sort of steric requirements of the substrate. So take ourselves now to around 2009, 2010, and Steve Newman, a grad student in the group now at the University of Ottawa, managed to use this observation to crack a long-standing problem for us. We had been developing, a guy named Eric Fang, a PhD student, had been developing a way in which to make indoles. But the one kind of indole we couldn't make was a 2-bromo indole. And Steve reckoned that if we took the ligands that Hartwig had used, perhaps we could get reversible oxidative addition. And this, in fact, was achieved, but it did require tri-T-butylphosphine. But it gave us access to compounds that were very useful. But even better than that, it led to another idea. And the other idea was, well, if oxidative addition is reversible, can we combine reversible oxidative addition with some other reaction? So for instance, this carbohalogenation reaction. And Steve developed this reaction based on the QFOS ligand. We did some computational work with Ken Hauk's group, who helped us to understand the details of this reaction. And in fact, it's a long story not to be told here, but we submitted it to Science. It diddled around for a while, didn't get published, and got accepted into JACS sort of just in time, since it turned out another group, the Tong group in China, was working on a similar reaction on a slightly different substrate with very different catalysts. In any case, it represented an important first step for us. And here's just a few examples, and this is where it takes us to oxindoles. So amongst the substrates that Steve investigated were 5- and 6-membered rings, oxycycles, nitrogen heterocycles, and most importantly, there it is, the oxindole. And it turned out those oxindoles are very popular in a number of pharmaceuticals. And so it made us, it turned into a kind of black hole of research field for us, where over the last 10 or so years, many different group members have attacked this problem of oxindole synthesis using many different methods. And that's what I'm going to share with you today. So the next player was Dave Petroni. He's a PhD student in the group who did a postdoc with Eric Carrera. He had a great idea where he took 2 iodo-containing compound, a compound with 2 carbon iodine bonds, both of which turn out to be equally reactive. And if we took traditional catalysts, we got essentially a very poor reaction, because one carbon iodine bond is just as reactive as the other, only when one reacts, it's a dead end. That's the structure that's shown over here on the left. That's a dead end unless you use the kind of ligands that Steve Newman, following the Hartwig protocol, had developed. And it turned out that that would allow the reaction to be reversed. And if it was reversed, the other carbon iodine bond could react, and that carbon iodine bond could go on and do a carbopalladation. And so what we could do was take this diiodo compound, treat it with palladium QFOS, and get the diiodo product where we'd functionalized only one of the 2 aryl carbon iodine bonds. But if we swapped and added a second acceptor, then we could actually react both carbon iodine bonds, but in very different ways. So this was a really important discovery from Dave. Okay, let's now talk about other aspects of oxindoles. For instance, what happens about spirocyclic oxindoles. So the next player was Dr. Hyung Yoon, who's now with Scott Miller at Yale. What Hyung was looking at was this carbopalladated product. And if you look at that carbopalladated product and you think about what the different R groups can be, our previous work really used R equal to alkyl groups. So the question we asked was, if R is equal to an aryl group, can we see a CH functionalization? Could we get some sort of intramolecular CH functionalization to make a palladicycle? And maybe that palladium species we could then react with things. It turned out that was true. Hyung could isolate that compound. In fact, he was doing detailed mechanistic studies, and then he was also interested to see what kind of pi systems could undergo reaction. And our first choice was actually arynes, benzynes. We've liked those for all sorts of reasons over many, many years. He wasn't especially lucky in this case, because somebody else was interested in it as well, and that was Garcia Lopez's group. And they published a very nice paper in Angewandte in 2016, just as we were writing up our paper and finishing the last of the experimentals. But what Hyung had done that was really important was to analyze that Palada cycle and to learn more about its reactivity. And because he was able to do stoichiometric studies, he was able to learn two things that turned out to be really, really important to us. So he did get a publication from his study with the arine, and we agreed to collaborate with the Garcia Lopez group, and we talked about what was next, and we were going to look at alkynes. And they said, well, we've looked at them, excuse me, and they didn't work particularly well. But we said, well, that's interesting because in fact, ours had worked very well. And the difference turned out to be the substituents on the alkyne. So if you use, for instance, disilol or diaryl, the reaction's very poor. But if you use electron unbalanced alkynes, where you have an electron withdrawing group on at least one end, then the reaction works very well. And again, thanks to Hyung doing these careful studies with the Palada cycle, we could actually explore that in some detail. And so, in fact, he was able to get this to work well. Here you see just a few of the substrates, which include things like esters are tolerated, alkyl groups are tolerated. A pyridine, a 2-pyridyl group, is as good as an electron withdrawing ester. And the aryl groups that you could CH activate onto included regular aryls, heteroaryls, and a number of other substrates. So this methodology turned out to be quite general, and finally resulted in Hyung getting the paper in Angewandte that he'd been eager to get. Okay, let's move on now to another class of oxindoles. What about methylene oxindoles? So here the next player is Christine Lee. She's now a faculty member at York University, not so far from me here in Toronto. And what she identified was a paper by Lee where they'd done a kind of a carbonylative cyclization reaction. And she was also working on this carbohalogenation and looked at it in two different respects. The first was with a very bulky alkynyl system, and her key contribution, I would say, was to think about the carbamoyl chloride group as a potential reactive functional group for this reaction. And she did a spectacular job identifying that with palladium 0 and certain very bulky ligands, these adamantyl phosphines, she could obtain a chlorocarbamylation. Now, what was surprising was, in fact, it was a trans addition, and we went through a lot of work to understand that. And that turned out to be great because she and Teresa Sperger, who was a PhD student in Francesca Schonebeck's group, worked on this together. And so the two of them looked at this from a synthetic and mechanistic perspective, and they identified the origins of some of this selectivity. Of course, she was also keen to make a cis-selective reaction, and then she turned to a different idea. Instead of palladium 0, she looked at palladium 2. And this palladium 2 actually turned out to be a chloropalladation followed by a cyclization. And so we could access these very, very interesting chloromethylene oxindoles. So that turned out to be a great study for us. And this just kind of shows the point. What she and Teresa were able to determine was that it's a cis chloropalladation followed by a cyclization of the vinyl palladium onto the carbamyl chloride. And you get some idea of the sort of diversity that's possible in this system. We could have various substituents in the left-hand ring, the blue R group. We could have different orange aryl type groups, and we could have different substituents on the nitrogen. So here's just a few examples to sort of illustrate the point. What she also did was to scale this up. So we made several hundred milligrams of that species and then said, let's see what we can do with that carbon-chlorine bond. That turned out to be really interesting. So we could add in a conjugate fashion, a sort of an addition elimination fashion. We could add amines. We could add thiols or thiolates. Maybe not so interesting, we could just ditch the double bond and the chlorine. And this was something that we still need to go back and investigate. If you did a kind of Suzuki-like reaction, it turns out it's probably not a Suzuki reaction. but you could get addition of aryl groups again with but this time unexpectedly with inversion. So that turned out to be something we need to still play around a little bit more with. Well, I mean, Christine's study kind of set us off on a number of different directions. And you can see at the bottom, just this year, this is one of our pandemic publications. Austin Marchese, Igor Laren, and Bijan Marabi are 3 grad students who decided to cover all the different ways we'd made oxindoles. And so they've written accounts of chemical research. So this kind of highlights some of what was done. Okay, so there's what I just showed you that, that Christine had developed. So the next question that came out was, well, could we do it instead of with palladium? Could we maybe do it with copper? Money's a little tight in Canada. We don't have a European Research Council. God bless us if we did. And so we had to figure out what to do. So we decided to look at copper. And this copper borylation has been looked at, especially by Hasomi Ito and Amir Hoveda, former colleague of mine from the Evans group. And they've done some amazing things, as you will be aware. We actually wrote a review on that as well that's appeared in ACS Catalysis. So the idea was, could we do a boryl cupration and then trap that same kind of carbamoyl chloride? Could that give us access to these oxindoles, but now we'd have them in an enantiomerically enriched form if we could do that copper borylation? And for that, we could actually turn to some other very nice work by the Brown group. You can see here, boryl cupration followed by trapping with an acid chloride. Here's an example from the Zhang group, and then came this paper from Andrew White from our group. So the idea was an antioselective boryl acylation, or actually carbamylation maybe is a better term, but we would make a boron carbon bond, and we would make a carbon-carbon bond. So there's Andrew. He's now a postdoc in Wisconsin with Teshik Yoon, and he developed all kinds of chemistry, and I'll tell you about just a little bit of it today. So what he found was that if we took copper, this chiral ligand, B2-pin2, and sodium T-butoxide, we could activate the boron, we could boryl cuprate, and then trap with the carbamoyl chloride. And the enantioselectivities were really very, very good. Here's just a few examples of different kind of substitutions. It's nice that you can have a heterocycle like a pyridine in there and still maintain good EE. You can have electron withdrawing and electron donating groups. We got an X-ray structure just to make sure we knew what we were talking about. And we could even have, instead of aryl groups, we could have heteroaryl groups and alkyl, though in the case of alkyl, the EE suffered a little bit. Andrew sort of turned this into a cottage industry of different kinds of reactions that we could do with this benzyl copper species, which is enantiomerically enriched from the original boryl cupration. And he showed, for instance, we could cyclize onto ketones to make cyclobutanols. Turned out that was and we could do so enantioselectively. We could react with to make these polycyclic indolines, which are quite interesting substructures of a number of natural products. And we could do it in a sort of an exocyclic fashion where we could boryl cuprate and cyclize to make some gamma lactams. Okay, so as I said, money was not in abundance. We were looking for cheaper ways than palladium and some of these expensive ligands. And so one of the first things that Steve Newman and I had talked about was, could we find a way other than palladium to do a carbohalogenation? And the idea was always to use nickel. But I must tell you, there's the example that Steve reported. And so I must tell you that thanks to some beautiful work from Jacobson and Hiyama, it was known that nickel could do this kind of transfer cyanation where we would transfer from an aryl cyano to an alkyl cyano group. So we wondered, well, what about a nickel version of it? And this was as well Hyung Yoon and Austin Marchese who looked at this. Now, the reason we discovered this reaction was because of Hyung's careful work with isolating these palladicycles. Because when he tried to isolate the equivalent nickel cycle, he got the carbohalogenation. And I won't tell you how much work went into it from that initial discovery to finally achieving it, but these are the optimized conditions, our initial optimized conditions. So catalytic phosphine nickel iodide, manganese as the reducing agent in toluene gave us access to these under conditions that are, of course, much more convenient, much cheaper to use triphenylphosphine than to use tri-T-butyl or QPhos. So the reaction's scalable, it tolerates all kinds of substitution, different substitutions in all the different places. So nothing really too surprising. When R gets very bulky, like an orthotoluol group, the yield does go down, but otherwise it's all good. We did get some enantioselective results, and this is a good story for students. It's a good story for professors for that matter. Hyung and Austin each took a different enantiomer of BiNAP, and they came back and they said, actually, one of them worked and one of them didn't work. It was like one gave EE and the other one didn't give EE. It's like, that's impossible. So then they went and looked at the NMR spectra of the BiNAP, and it turned out there was some BiNAP O in one of the two enantiomers. So one of the phosphines had gotten oxidized, the other one was not oxidized, and the one that had the BiNAP O was the one that gave the decent EE. So that was a bit of good luck, let's be honest. Never hurts to have some good luck along with a bit of hard work. And so I won't tell you the whole story, but it turns out it doesn't really need to be BiNAPO. It just needs to be a donor. So it can be triethylamine, it can be even triphenylphosphine. It just needs to be another donor ligand in order to promote this reaction. And though it wasn't perfect, it was pretty good. It was a start, and better than we'd ever been able to do in the case of palladium asymmetric carbohalogenation. So there's the results that I was just describing to you. So what we wondered was, could we combine this idea of Christine Lee's using the carbomoyl chloride and sort of the boryl cupration idea, but maybe now do an asymmetric nickel reaction? And this was the concept that was in play, this kind of alkenyl carbomoyl chloride. Now we can't really do a carbochlorination, only a carboiodination. So we added iodide in there, and now we could achieve the reaction that's illustrated. So nickel diiodide, we used a chirophosphine ligand, manganese, and Ki, because we have to terminate the reaction with C-I bond formation, not C-Cl bond formation. But this is really a major improvement for us over what we'd been able to achieve with palladium. And in addition, it was a nice way in which to access these oxindole compounds, again, with chirality and with still a functional group handle that we could do additional work. And this project was another nice collaboration. We have a collaboration with the University of Munster. Frank Glorious' student came to join us, and we've published this together. So that was a transatlantic effort. What can we do with these products? Well, Austin really pushed this along ways. We could displace the carbon iodine bond with cyanide. We could reduce it and also reduce the lactam and end up with this nice tricyclic compound. At that point, we were able to do a reductive alkylation to introduce the N-methyl group. Oops, I'm sure I got that right. There we go. Then we could cleave off the methoxy group and then functionalize that methoxy in two different ways. So we could end up making 4 natural products from one common carbomoyl iodo functionalization starting material. Okay, just in the last few minutes, I'm going to switch away from nickel, copper, and palladium and tell you a little bit about rhodium. Tamio Hayashi developed a nice functionalization reaction using alkyl zinc species, where you alkyl rhodate and then cyclize to make methylene oxindoles. And so 2 people in our group, Alvin Zhang and Hyung Yoon, had looked at this concept in terms of conjugate addition and cyclization. We actually thought we were going to need 2 metal catalysts here, but 1 turned out to be good enough. But we could never render that reaction enantioselective. So we decided to try a slightly different approach where we'd use this alpha-beta unsaturated amide and try to do a conjugate reduction and then a rhodium catalyzed CC bond formation. And there's Alvin. He's just finishing up with Tom Rovas before he starts with at AbbVie. And he and Igor developed a beautiful number of examples where they could get high enantiomer selectivities through this conjugate addition, and then rhodium, which is not normally so good at inserting into CX bonds, when it's directed, it is able to do so. Okay, the very last thing I want to show you, I told you that we got interested in multi-catalysis. So this is the way chemistry has been done for a long time. People, of course, do flow chemistry. We said, well, what about if we could mimic nature? What about if we could just put everything in the pot all at once? Could we cover all the reactions in one go? And we looked at this in a number of different ways. What you need is kind of orthogonal reactivity, and you need timed reactivity where you get selective conversion one step after the other. And that very much mimics the way biology is happening. So this is one last homage to Barry, of course, the allylic alkylation. So what we decided to look at was, could we take a diazoamide, do a CH activation, and then do a palladium asymmetric alkylation reaction? And indeed, that's what we were able to achieve. The CH activation, we tried a number of metals. Ruthenium was the best, and palladium, of course, was the best for the allylic alkylation. And you can see we threw in a Trost ligand, and so we could get this palladium plus ruthenium. In this case, we have ligands for the ruthenium, we have chiral ligand for the palladium, and the EEs of this are okay, they're not great. This is about the best people can do in this asymmetric allylation. In fact, Barry had already done that kind of reaction. And so we really were showing that we could put two metals, two ligands, one substrate, and do multiple reactions all in one go. So that takes me to the end. I think I'm within a minute or two of on time. I hope so. We looked at all different metals, but we always had one goal in mind. How could we make an oxindole? And that's because they turned out to be a lot more interesting than I ever imagined when we started the project. But there are so many different oxindoles out there, and they can be attacked in so many different ways that I think they merit their attention on their own. I'll show you some pictures just at the very end. Of course, the funding is crucial. You can see pictures from 2012. That's around the time that this project started. And there's Steve Newman. There's Dave Petroni. Hyung makes his appearance a number of times in here. Andrew White. And the most recent picture, of course, now if we had a picture, there'd be 15 of us standing in 15 different places, 2 meters apart from one another. Just on Nuno's point, I agree 100% that it's important for scientists to reach out. And around about 2017, I took let's call it what's it called? When you work at night, you know, when you work after hours doing something you're not supposed to do. Well, for me, that turned out to be writing opinion pieces for the newspapers here in Canada, trying to get our politicians to pay attention to funding science, to helping young people, to recognize how important it is for grad students and postdocs to be supported, and actually for scientists to go into politics. I have no intention of going into politics, but I strongly encourage some of our young and bright minds to keep speaking out for the many kinds of injustices that there are, and to make the world a little bit better place through science. So on that note, I will say thank you all very much.
Thanks so much, Mark. That was great. Learned a lot about oxindoles that I had not known before.
That you maybe never wanted to know.
No, that I wasn't going to go that far for sure. We have one question from Assem Barakat. Your starting material amide is a tertiary amide. I think they were all N-methyls. What about secondary amides, or maybe even other groups on the nitrogen that one could remove easily later?
Yes, so I didn't show those examples. Sometimes the NH compounds themselves don't work. Sometimes you do need to have a substituent on there, but we've put, let's call them protecting groups instead of just substituents like PMB and things. And we've been able to remove those protecting groups. So yes, it's true. The examples I showed were kind of limited, but in fact, it's much more general than what I implied.
Awesome. I think I'm trying to monitor the chats, but I don't think I see any other questions at this point. Okay, well, one just came in. Were there attempts made to go from indoles per se to other derivatives?
You mean in terms of the coupling to make, when we made, say, these brominated indoles? We have looked at that a little bit, although not as much detail as we probably should have. We initially tried to make the 6-membered ring analogs. That didn't work out as originally drawn up, but we haven't gone back to it since we developed some of these new catalysts and other methods. So that's a very good idea, but we actually haven't played with that.
Okay, so now the questions are pouring in, Mark, so I'm going to keep you for another couple minutes. So how stable are the spiral oxindoles, for example, on a column?
Young never cursed when he told me he'd purified them, so I'm assuming they're okay, but I'll be honest with you, I haven't run a column in a couple of years. I think I was last in Dave's group, but yeah, so I think they're stable, certainly once isolated, and I don't remember hearing anything too bad about them.
Okay. And there's another question about converting the OH to a triflate, and was a Suzuki tried in the oxindole?
We have not tried that. It's an interesting idea. No, we did not try that kind of reaction.
Well, seeing no further questions, I want to thank you for a spectacular talk, and obviously Nuno and Janine as well. We are going to reconvene in about 10 minutes. So we're going to take a short break for everyone, reconvene in 10 minutes for Professor Trost's lecture.
Hi, my name is Phil, and I'd like to wish Team a happy 20th anniversary on the Science of Synthesis series, which has been an essential part of our laboratory's library for a very long time now. We use the online version, we use the text one, as you can see right behind me. And it has been a really integral part, at least of my life, in the way I go about brainstorming for projects in the laboratory, finding literature which is sometimes very obscure and hard to find on SciFinder, or for solving very difficult consulting problems. So I'm really grateful to Team A for putting together this amazing series and continuing this wonderful tradition. It's a huge help to the community. Fantastic trove of information which you may not be able to find anywhere else, and it's so beautifully organized, and thank all the contributors over the years for their diligence and hard work in putting this together. And I wish you all hopefully another 20 or 30 or more years of great success in putting this series together. Happy birthday.
Hi, my name is Margaret Fawn. I work at Amgen, and I've been a member of the editorial board of Science of Synthesis since 2018. I would like to take this opportunity to congratulate Theme Chemistry and the Science of Synthesis on their 20th anniversary, and to thank the Theme and Science of Synthesis team, the editors, and all of the authors who have contributed through the scientific community through the publication of this journal. As you're aware, the Science of Synthesis occurs in both hard copy and online versions, and for me, I find it's really well organized and it's easily searchable. It provides critical reviews of organic chemistry transformations, but also a feature which I particularly like is it provides the detailed experimental procedure for performing many different reaction types, which is extremely valuable whether it's a new chemist starting in the lab or an experienced chemist that's working in an academic or an industrial setting. Science of Synthesis over the last 20 years has truly become that foundational single source of truth for organic chemistry transformations, and has been an amazing contribution to the scientific community. With that, I congratulate you on your 20 years. I wish you the best, and I look forward to many exciting contributions and many additional contributions in the future.
Hi, this is Shuli Yu from SLC. This year will mark the 20th anniversary for Science of Synthesis. I would like to congratulate to Team Chemistry for doing such a great work over the years. Science of Synthesis is a unique reference work which covers all methods of organic synthesis, offering the full text descriptions of organic transformations together with validated experimental procedures. I really like this feature, which saves us a lot of time during our research. The online version is also really amazing and entirely searchable based on the structures, substructures, and reaction types. I was fortunate to join the editorial board of Science of Synthesis early 2018. I would like to thank the Team Chemistry team, all the editors and authors for their hard work. I wish the Science of Synthesis keep doing great and maintain such a high level of excellence in the years to come. Happy 20th anniversary, Science of Synthesis.
Okay, I'd like to welcome everybody back for prime time here at the SOS anniversary and dedication to Professor Trost. So Barry received his bachelor's degree at the University of Pennsylvania. And at least one of my colleagues, Madeline Juliet, remembers him as a nice young boy from Philadelphia. He went on to receive his PhD at MIT with Herbert House, and then went directly from there to University of Wisconsin, where somewhat remarkably to me, and perhaps many others, he was a full professor by the age of 28, and was in the National Academy at the age of 39 when I was a postdoc there. Subsequently, he moved to Stanford University and obviously has had a spectacular career. I'm just going to highlight a few things. Not all of his awards, because he's got so many that would take all of his time. But in my mind, I mean, one of the distinguishing features of Barry's career is that he was really one of the pioneers in homogeneous catalysis. You know, starting with Barry Trost, a little calculation reaction, and well beyond, and really one of the pioneers also in asymmetric synthesis. But perhaps more importantly, he was probably the first and maybe most predominant person to articulate or express with any coherency the ideas of and the importance of selectivity, chemoselectivity, regioselectivity, and stereoselectivity, and of course, atom economy in doing organic reactions. And just, I was going to spend a weekend counting the number of coworkers Barry has had, but I gave up. So I'm going to estimate, but I'm sure it's over 500 coworkers, obviously from all over the world. The influence he's had is universal in academia and in industry as well. And I can say as a former postdoc that I would not have achieved anything that I've achieved without his mentorship. And I think many of us feel the same way. So Barry, I'll leave it up to you, and you're going to talk today about chemistry and biology merging sciences.
Thank you very much, Gary. Can people hear me? Oh, wait a minute.
You're on.
Let me get my slide deck up. So I have to share the screen.
Yeah.
Here.
Yep.
Share.
Yep.
And then go here.
Yeah. Perfect.
Okay. Now we're ready to for me to present what I'm trying to say to you. Today, I would like to show you how my research program evolved from thinking about the interplay of chemistry and biology. While biology began as a phenomenological cellular science, in the early 19th century, leading scientists like Berzelius in Sweden, in his lectures in animal chemistry, stated that organic chemistry is the part of physiology which describes the composition of living bodies and the chemical processes which occur in them. So here we're talking about the chemistry aspect that one usually would associate with biology. He elaborated that such chemical processes involved what he termed as catalysis. When he wrote, "We have justifiable reason to suppose that in living plants and animals, thousands of catalytic processes take place between the tissues and the fluids and result in the formation of the great number of dissimilar chemical compounds, for whose formation out of the common raw material, plant juice or blood, no probable cause could be assigned." So here we are really talking about, are these separate sciences or are they just various parts of the same? These thoughts started biology on its course of understanding living systems on a level that probed beneath the phenomenological cellular one, and led to the appreciation that a greater range of biological function beyond the chemical reactions that occurred were also molecular in nature. The use of small molecules to manage these complex molecular processing to bring benefits to plants and animals then becomes a major objective. Designing such molecular structures for maximum benefit, regardless of structural complexity, is possible only if we have the synthetic tools to access them in a time-efficient manner, a requirement that means we need the synthetic methods that meet such a requirement. This became a major objective of my program. We wondered how we might put together the ways by which you can construct relatively any type of structure for the function that you're trying to look at. And synthesis is the key. Synthetic efficiency consists of, first and foremost, selectivity. As Gary has just mentioned, we became concerned of how you can utilize chemical catalysis to have good ability of differentiating among different bond types. That is, to be chemoselective, how they can orient how reactants would interact with one another. That is regioselectivity. And then, of course, there is the stereochemical selectivities, where you're controlling relative stereochemistry or diastereoselectivity, and absolute stereochemistry or enantioselectivity. But selectivity, although it is an extremely important part, it's not the only part that's important. That another area which we termed atom economy is one that is also of great concern to us. And in doing so, what we're asking, can we develop reactions that 100% of what goes into the flask ends up as product? And we then in this way be environmentally benign by design. And in trying to do this, you could ask, can we take existing methodology and make them more selective and atom economic? But we can also ask, can we have new paradigms of reactivity that are stimulated to design the synthetic process that will indeed intrinsically become atom economic and selective? The area that we started with was a very fundamental process, and that's simple alkylation chemistry. You have a leaving group that you depart with a nucleophile, and this is especially activated if you have a double bond adjacent to the carbon bearing that leaving group. And in this way, you can undergo allylic alkylation reactions where you would then substitute that leaving group, introduce a new nucleophile with an inversion of stereochemical configuration. We wondered whether by the use of catalysis, we could indeed add to this simple version, which does not employ catalysis, to make the overall process more widespread in terms of scope. That with a catalyst, for example, could we carry out a substitution not with inversion, but with retention configuration? Could we carry out reactions in which the new bond that's being formed is not necessarily being formed at the carbon bearing the leaving group, but it could be formed at the allylically related carbon? So we could have a broader range of scope in terms of stereochemistry and chemoselectivity issues in carrying out the synthesis. And we had turned to palladium chemistry and showed that it could be a catalyst for a lot of the aspects of allylic alkylation. That palladium, palladium 0 species could function as a nucleophile to substitute that leaving group, and in that way it forms an allyl palladium complex. So you have the palladium not bonded by a single bond to carbon, you have it as in a pi allyl form. This process of the substitution of the leaving group by the metal then presumably would have occurred with inversion of configuration, but then the substitution of the palladium by the nucleophile would also occur with inversion of configuration. And in that way, the overall process then becomes one in which you have a net retention of stereochemistry by using metal catalysis. Also, the fact that you are looking at an intermediate where the attachment of the leaving group is no longer a factor, that it's now a pi allyl, the ability for you to then direct how you would introduce the nucleophile, which regiochemistry could you obtain? Would it be at the termini or perhaps even at the central carbon? And in fact, any one of the 3 carbon atoms can be activated for nucleophilic addition reactions. And so one has here really a much broader scope process by introducing the concept of metal catalysis. But the most important one that we were trying to get at was the one dealing with stereochemistry. How could we carry out asymmetric catalysis? Now, the problem here comes from the fact that in the ionization event, this occurs on the face of the palladium, which is opposite from where the ligands reside. And similarly, any bond making and bond breaking events are occurring on the face of palladium away from where the ligands reside. But where the ligands reside is where your stereochemical information is going to be. So how can we transmit stereochemical information from one side of the palladium to the other side? And here we took a lesson from biology, where in the case of enzymes, what they did was to fold themselves so that they would have active sites. And it was how substrates could fit and move within those active sites that these enzymes were able to affect catalysis with such selectivity. And we wondered, is there a way that we can create a similar arrangement with a much, much simpler system? And in particular, using phosphine ligands. If you have 3 aromatic rings attached to phosphorus and look conformationally how they would reside, they can't reside in a planar array, that the interactions of these aromatic rings will force them to twist. They create a helix, and that helix can be chiral. And so one could ask the question, could you adapt the conformation where what you're seeing here is a edge face interaction between the aromatic rings in this helix. And as those aromatic rings are organizing, you can get a right-handed or a left-handed helix. And it is within this active site that is depicted on the cartoon at the right. And it's how the allele system and the incoming nucleophile can fit and move in this active site that would give rise to the chiral recognition and hopefully good levels of enantioselectivity. There was subsequently some nice computational studies of our reaction by Guy Lloyd-Jones, in which he noted that there are interesting aspects of the structure that could be indeed supportive of this type of a picture, where if you have a case where it's going to be the ionization of the leaving group that's going to be an antiodetermining step, this could arise indeed by having, whoops, where's my cursor? By having that leaving group be hydrogen bonded to this secondary amide. And that hydrogen bonding interaction is then a chiral event. On the other hand, you could imagine that you can have the chiral event be the nucleophilic addition. And here too, Guy Lloyd-Jones's calculations suggest that as a nucleophile would be approaching, it again could have that interaction with that amide NH. And that could then take the nucleophile on a tour to the proximal allyl terminus, and in that way would control the absolute stereochemistry. So you have mechanisms of being able to introduce chirality that makes another advantage of this type of approach for carrying out chemical reactions. And this is something that really makes it very helpful if that can be coupled with a wide scope. So let's take a look at some of the mechanisms by which it can induce that stereochemistry. The simplest system is having something like a crodal system. And when you have a crodal system, you have an antiotopic faces associated with the double bond. And the metal with its attendant ligands then can complex either the top face, as on the left, or in the middle here on the bottom face. These are the enantiotopic faces of that olefin. And if you get ionization from these enantiotopic faces selectively, you generate the 2 diastereomers, because it's the catalyst is chiral, the allyl unit is chiral. So these are really now diastereomers and not enantiomers. And it's the ability for the one on the left to be formed selectively or the one on the right to be formed selectively, which determines the stereochemistry of your product. And so we started to engage in carrying out the actual synthetic events that might lead to biological applications. Natural products could be an example of this, and the chromans, like this clusiofoliol, would be an illustration of a simple case where you just have a tertiary center bound to oxygen, and it's that stereo center that you're going to create by a palladium catalyzed ionization. More complicated molecules like cyconine can also be reduced down to a similar type of thing in trying to create the stereochemistry that one is seeing, at least in part in cyconine, where the substrate that you're going to be involved with is the one shown at the bottom here, where you have this tri-substituted double bond. It doesn't matter what the geometry is. It could be either one, but it is then the ionization of that system which gives rise to your selectivity in determining the chirality of the chroman portion of the cyconine molecule. At the same time, one also would have the notion that these pi-allyl metal intermediates, which are diastereomeric, as I mentioned, these could undergo rapid interconversion. So it's not their formation, which is determining the enantiomer-determining step. It is the rate of attack of the nucleophile on these two different pi-allyl metal complexes. And the notion here is you have to have that be fast. And that the enantiomer-determining step then is the nucleophilic addition. And so again, we look to show that this really has broad applicability. So that if you want to make a chiral drug, for example, that allylic alkylation chemistry is a very powerful way to make the compounds that you would have in mind. So we've taken a wide variety of biologically active compounds, or compounds who have known biological activities, be they natural products, or in some cases, be they synthetic compounds, and in fact, some of these are actually drugs, and that can one use as a unifying theme the ability of generating very, very broad structural diversity by having at the origin an asymmetric allylic alkylation reaction. It's pretty obvious in the case of something like vigabactrin over here on the left, that the way approach of this is using this monoepoxide of butadiene. That stereocenter upon ionization of the CO bond is gone, and we now have the circumstance of these types of pi-allyl palladium complexes rapidly interconverting, and then in this case of the vigabactrin being attacked by nitrogen, and in that way you formed this secondary amine. Now, one of the interesting aspects of this process was the fact that you could use a second vinyl epoxide that in the case of an amine could allow you to carry out the introduction of two of these side chains. And that this can be the same as I've used here. I've used just the same butadiene monoepoxide, but potentially they could also have butadiene monoepoxides which have additional substituents. And carrying out their introduction sequentially would allow these two to remove the symmetry that's present. You could have two quite different structural types. One of the things that this leads to, however, is that you have this diolefin, which is set for a metathesis reaction. And that allows a cyclization to generate the corresponding 5-membered ring nitrogen heterocycle. And this is a very useful introduction of those two stereocenters at the 2 and 5 positions of the ring system. But you also have a double bond. And as you can see, there are a wide diversity of these corresponding pyrrolidines in which you have heavily substituted systems. In this case, have every carbon atom substituted with functionalities that play important roles in biological applications. Things that have these hydrogen bonding interactions with OHs, with NHs, that can lead you to particular important interactions as they are trying to affect the what is carrying on under biological conditions in plants and in animals. Another mechanism for introducing stereochemistry starts with a chiral allylic leaving group. In this case, the allyl system has at the termini the same group. In the case I'm showing here, it's just the methyl group. And that is important because ionization of that leaving group, then creates the pi-allyl intermediate. And this pi-allyl intermediate in this case has a plane of symmetry. It has no chirality. And so one can induce chirality by having the nucleophile attack one of the termini of that allyl unit. And indeed, this mechanism has proven to be also a mechanism having very broad scope in the kinds of structures that you can access, that it can constitute the kinds of structural variations that you would imagine that if you're going to design a good drug or a good agrochemical agent, that you can define a complex structure or as complex as you think is necessary to have the reactivity that you want. And just look at the functionality that one can generate in the products by using this kind of allylic alkylation chemistry. It might be noted in these examples that a common theme is this six-membered ring. You can see this in the structures at the bottom of the slide. And in these cases, you notice that we have an allyl alcohol and we have another substituent here. Now there's a relative stereochemistry between those two, and that stays in the molecule so that you could have them be either trans or cis, either way. But it is a case now where ionization of that leaving group, which is the OH group, where is my cursor? I always lose my cursor. Where are you? There you are. That when you ionize this leaving group, the entity that you create has a plane of symmetry. Has a plane of symmetry passing through it. So it's one or the other allyl terminus, which is going to determine the chirality. And indeed, that has been used in all of these six-membered ring cases. And let's just take the last example, Tamiflu. That's an important drug. And that drug now can be readily synthesized by forming that CN bond, using just such a system where you have, in this case, the leaving group attached to a carboxylic acid, so you have a lactone, and that controls the relative stereochemistry between the leaving group and that carboxylic ester unit. And when you carry out the substitution, you then generate the allylic amine asymmetrically, and the double bond of that initial product is exactly situated where it is what you need then to carry out. Again, I'm sorry, I'm losing my there it is. I'm losing my pointer. That it has here a carbon-carbon double bond initially, and that's where you need to elaborate introducing this nitrogen and that oxygen. And indeed, the net result is this strategy is a very efficient way to create Tamiflu. And it's one of the best ways to synthesize this very important drug. Another mechanism that involves the nucleophilic attack as the enantiodiscriminating event is to start with a meso substrate where you have two allylic attached And that it is, again here, which of these leaving groups is going to be activated. And that then is the ionization event being an antiodetermining event. That if you ionize the one on the left, you obtain 1. If you ionize the one on the right, you turn the mirror image. And then again, as you can see, this ability of doing this has broad use, and that one can make a very large number. And these were done with 5-membered rings because the intermediates are very readily available. You take cyclopentadiene, you take singlet oxygen, and you have access to this core structure where that's a carbon atom. It doesn't have to be a single carbon atom. It can be multiple carbon atoms, in which case, instead of getting 5-membered rings, you'd get 6-membered rings or 7-membered rings. That this can also be heteroatoms. So it can be, for example, a sulfur, a nitrogen, but especially an oxygen. And again, these are the kinds of structures that you can see examples of in the examples that I show you on this slide. So we again have a process here which has a wide diversity of scope. And as you can see, the examples are also ones where they have a wide scope of different types of biological effects that one is seeing in these reactions. So we believe that this part is an unusual opportunity to be able to make almost any kind of structure you can imagine when you're trying to design structure for function. There's one last method for analysis, for achieving asymmetric induction. And that is, instead of looking at it in terms of the allyl palladium species, looking at it in terms of the nucleophile, that the nucleophile could have chiral faces, and that this too can lead to a vast array of structures that become possible very readily by using induction of stereochemistry at the nucleophile. Now, one of the common aspects of this chemistry is the kinds of nucleophiles that are employed. And in these examples, they all have at their core that the nucleophile in which you're going to introduce stereochemistry is an enolate. So for example, if you have these aminals, so on the structures on the right, that they would evolve from somebody's, I think, who has an interest in oxindols. They have this oxindole as a key structure where you can do an asymmetric allylic alkylation reaction, and in that way then have a further elaboration into these alkaloids that are shown on this slide, for example. Or you can have a target like the one on the left, metastazine. This is also a case of an enolate structure because that comes from a beta tetralone. You take a beta tetralone, you then can do an asymmetric allylic alkylation, and that introduces what will become that 5-membered nitrogen ring, and introducing or controlling the overall stereochemistry in a very, very convenient way for the final elaboration into this natural product. So one does have a great possibility to solve problems at will. Now, while allylic alkylation reactions are very powerful processes, there's also a lot of opportunity if we can have new methods for putting together complex molecules, which can be designed from the beginning to be atom economic. And in this category, we paid attention to the involvement of acetylenes as key building blocks. Because one of the advantages of acetylenes is the ease by which the acetylene is amenable to undergo reactions by simple additions, whether it's additions to the pi system or it's additions to the acetylenic CH bonds, that these are intrinsically atom economic processes. And one such reaction that we got involved with is the reaction of alkenes and alkynes. And in looking at alkenes and alkynes and a coordinatively unsaturated ruthenium, you can imagine that the ruthenium and the alkene could coordinate with one alkene and one alkyne. And by so doing, it would create this complex, which could undergo a tautomerization and thereby generate a metallocycle. And that metallocycle sees at the beta hydrogen, by beta carbon, a hydrogen. So it could do a beta hydrogen insertion reaction, generating this vinyl ruthenium hydride, which undergoes a reductive elimination, generating a 1,4-diene, reforms the catalyst for a second go-around. And this could be a very useful approach to make complex molecules. Let's take a look. There is this antibiotic, pyrisidin A, which has attracted attention, and it's adorned with a very, very complicated side chain. And so we could imagine that you could have access to the side chain, having as an alkyne partner, the one shown here. And I use that because this is remarkably easy to make. It comes from 3 simple building blocks. It comes from the corresponding alkyne, the simple propyne, acid aldehyde, and this prenyl aldehyde. And these are mainly involving addition reactions that give rise to this particular alkyne. And that starts the process. We're going to react this alkyne with propene, not propyne now, propene. And that alkene-alkyne coupling with ruthenium occurs quantitatively and installs this allyl unit with complete control of regioselectivity and stereochemistry. Sorry, of regiochemistry and geometry, where you have, regioselectivity and geometry. So where you have still a monosubstituted alkene, which you could imagine could also serve as an alkene for a new alkyne. And so in the next step, we have the addition of this pyridine acetylene, which then creates exactly the side chain having the double bonds of the right geometry and positional control. And that after removal of protecting groups, you have a synthesis of the pyrisidin that took 7 longest linear, 12 total steps. And to put things in perspective, there's a beautiful synthesis using traditional methodology by Lipschitz, and that required 11 longest linear, 18 total steps. So this does give you opportunity not only to be atom economic, but to make your syntheses more efficient. Now, Mark related to this in his comments about a reaction that he got involved with, which is also a reaction of alkenes and alkynes, but it was using palladium. And indeed, palladium, if the alkene and alkyne would be interacting in a intramolecular fashion, that alkene-alkyne interaction could be catalyzed by palladium. And one mechanism that is involved here is that using a complex which is formed by simply taking palladium 0 with acetic acid. And that palladium 0 can insert into that OH bond and generate the hydridopalladium acetate. And that now can serve to coordinate the alkene and the alkyne in the manner similar to what I showed you with ruthenium. But in this case, the next event isn't a metallocycle, it's a hydropalladation event where that palladium hydride does a cis addition to the corresponding acetylene, generating then a vinyl carbon palladium bond, which does a Heck reaction with the double bond. And now it does a beta hydrogen elimination reaction. And in that way, you have generated your 1,4-diene or potentially a 1,3-diene, depending on which of these beta hydrogens would undergo preferential insertion reactions. But this becomes a powerful way to achieve such cyclizations. And importantly, if you intersperse additional acetylenes, that you might be able to get a elaborative process where you can do multi-cyclizations before the termination step by the Heck reaction. And this is exactly what happened with the co-nocinolides, which are a class of terpene of quite unusual structure. And in thinking about ways of making this rather unusual structure, we were influenced by what would happen if we would put into that target a double bond, creating a butenolide. Because if we do that, then we could see that this kind of triene substrate would come from a cyclization of this diene, that a hydropalladation, carbopalladation, beta hydrogen elimination of this molecule would then give rise to your targets. And what's very exciting is that this rather complex looking material is actually very simple. It's simply the ketal between acetone and propargyl alcohol. You form the ketal of propargyl alcohol, and you have these terminal acetylenes that you can elaborate with addition reactions, where you replace this CH bond by a carbon-carbon bond. So if you do that from this diene, you put on one end a carboxyl unit by either carbonylation or carboxylation chemistry, that then takes the other CH bond to do the addition to this aldehyde. And that can be done asymmetrically using a catalyst system that we have developed in my laboratories as well, this prophenol system, which is proving to be a very useful way for carrying out a lot of different addition reactions. And one of them is the addition of a terminal alkyne to a carbonyl group. And as you can see, you can get 95% EE. So one then can put together this tricyclic intermediate by taking palladium, acetic acid, and this is obtained in 65% yield. An asymmetric net hydrogenation of the butenolide then gives rise, after acetylation of the primary alcohol, to the acetoxy conocinolide target. And what's quite exciting, it allows you to obtain that natural product in 6 total steps from propargyl alcohol. Another advantage is you have easy access to other members of the family. So for example, we can take recognition that this butenolide is a furan, and a furan is a tautomer of furan. And so if you enolyze this, you put it into the furan tautomer, that is very susceptible towards oxidation by something like MCPBA. And in that way, you create this acetal, and that acetal, after the hydrogenation of the double bond, again, just as before, allows you to access the conocinolide E product, and that is done also in just 6 steps from propargyl alcohol. Now, there is another kind of reaction that one could imagine with terminal acetylenes and palladium. And in this case, it's what happens if you use palladium-2. I should say the dicarboxylate. That when you use palladium dicarboxylate with a terminal acetylene, that allows the palladium to form a carbon-palladium bond by the removal of the proton that's attached to the terminal acetylene. This now can undergo a carbopalladation of another acetylene, which could be either monosubstituted or disubstituted. And that carbamethylation would proceed in a cis fashion. This now can undergo protonation to cleave that vinyl palladium bond, and that way gives rise to this E9. So one has here yet another method by which you can do addition chemistry just by modification of your catalyst. The last end of this is the ability of taking a molecule like bryostatins and having an ability of making bryostatins, maybe in a manner that makes them more desirable because of their extraordinary biological activity. In our initial work, we were focusing on the synthesis of bryostatin 16, and we've published that quite a few years ago. But we focused on that one because it has this double bond in the C ring, the bottom ring, and that enol ether can either be oxidized, dihydroxylated, which then generates this family of the bryostatins. All these bryostatins come from just the variations of the alcohol esters, or it can come from hydration of this double bond, which gives rise to many of the other bryostatins. But what it doesn't take advantage of is an easy way to access the most complicated members of the bryostatin family, which has in addition a butynolide annealed to the C ring. So we imagined that we perhaps can have a way to access this kind of a target, and hopefully in a reasonable manner, considering the complexity of the problem. And so choosing bryostatin as the target, we could imagine that the bryostatin molecule can come from 3 building blocks. This black one that I showed here, which gave ring A, the pink one, which I show on the left, and that then is the diene, which is going to be a linchpin to join together the B system with the C ring system, the C ring system coming from this alkynoate. And if you look at this in the structure A, we have a double bond, and that double bond is going to react with this triple bond in structure B, and there is this less hindered triple bond, so we don't need to differentiate. We can have a diene, but the reactivity is very sterically sensitive. So this alkene-alkyne ruthenium coupling is going to form specifically this bond right here. And that then turns into ring B. And so one has created ring B very nicely by simply the alkene-alkyne coupling process. We still have the other acetylene, which after removal of the test system can undergo the reaction I just mentioned with palladium acetate, and that terminal acetylene would add to this propylate acetylene from structure C. And in adding that terminal acetylene to this internal acetylene, one then has a way by which you have been able to form this bond right here. And in that way, you've created both the pyran part of ring C and also ring D. Having this kind of manipulation of the alkyne metal chemistry, ruthenium and palladium, then led to a synthesis of bryostatin 3, which took 22 longest linear steps. and 31 total steps. To give you an idea of what you would do in terms of such a synthesis using more traditional methodology, there is one other synthesis that's reported, and the reported synthesis has shown it required 43 longest linear steps and 88 total steps. So indeed, atom economy, step economy is also at play in being able to use these acetylene-based strategies in terms of solving our problems of complex molecule synthesis. Well, with that, I'd like to point out that I am mainly a spokesperson, and I have had a wonderful opportunity in the 55 years that I have been involved in my efforts towards trying to make an impact on organic chemistry. It's because of the great group of people who have chosen to study with me. And they are numbering about 600 students over the years. So to all the students from 1965 to the present who made it all possible, I am deeply indebted to. And what is also quite nice about it is how much fun it has given us. Well, with that, I think I probably use my time, and I want to thank you very much. I have a small addition here because it just relates to the rather intriguing question that people in science today should be very much concerned about. Because many people say that chemistry, we know so much, there's really very little to learn. So you might say, do we have all the structures needed in order to make drugs? And the question to that would be, how many drug-like molecules are there? If you take Lipinski's rules, saying it should have less than 30 non-hydrogen atoms, and it should have about a molecular weight of 500, what you come out to is to a total of about 10 to the 62nd possible molecules. Now, how big a number is 10 to the 67? It is big. If we limit our sample size to just one molecule, not one mole, one molecule of each possible structure, you would have a set of molecules that would create a mass that would be equivalent to 100 million suns. That's pretty big. If you started at the time of the Big Bang to synthesize these, and you were able to synthesize them at the rate of 3 trillion per year, the fraction of molecules you would have make as of today is 1 over 10 to the 38th, almost nothing. Are there possibilities? Surely somewhere in that vast chemical space, there exist all of the best drugs for every disease. And our task now is to find them. So with that, let me conclude. And just saying that, you should be careful about deciding whether a science is mature. Don't do that. Because if it's mature, the next step is old age and the next step is death. And we don't know what we don't know. So how mature a science is can only be determined if we really knew how much knowledge exists there. And the amount of knowledge that we don't know is truly immense. Thank you very much.
Thanks so much, Barry, for that fabulous talk. And again, it brings out the vision, that you've always had. And I think that's been appreciated by everyone. There's been a number of people, number of former students among the 600 who have congratulated you and send their warm wishes. I think later on you can probably look in the chat. If you don't mind, there's 2 or 3 questions that I might pose to you if you're willing to answer some questions.
Of course, no problem.
One from Nick Greaves, actually. In the synthesis of conocenolide, how important were the gem dimethyl groups to the success of the cyclization?
Well, undoubtedly they helped. That's what you would expect. But I can't say that I think they have a do or die application. that the coordination of an acetylene with the palladium or the ruthenium is so good that I don't think having those two methyl groups, which would help favor the cyclization process, is critical for it to occur. So my take on that would be the reaction would proceed just fine with either no substituents or one substituent, as well as having two.
Okay. Another former trustee, Doug Tabor, asks, is the diastereoselectivity in conositolide cyclization a kinetic process, or is the reverse of the insertion into the alkene faster than the beta hydride elimination?
We don't have a clean evidence for which is occurring, but it's my strong suspicion is that the beta hydrogen elimination reaction, the last step, the hex step, is not reversible. So that it really is the kinetic effect, the kinetic one that you're seeing in forming that, that having the CH less hindered is really what's involved.
Maybe one last question. Why palladium for allylic substitution and so few examples with molybdenum? And this is from Arnaud Gauthier, who says, you made great discoveries in the molybdenum field.
Yes, I think Mark would have some comments about the molybdenum field. It is an area that I can say I know some drug companies who were manufacturing, or at least in the large scale efforts when they were getting drug approval using molybdenum. So the molybdenum is a very practical way, but it's much more limited in scope compared to the palladium. So it's really a playoff that if the molybdenum reaction does work in your system, it can be very practical, and it does give you a selectivity. It gives you a regioselectivity for reaction at the more substituted terminus, that you can indeed have a very efficient way of carrying out reactions, and probably we didn't play on the molybdenum as much as the palladium, just because the palladium was working so well, and we just don't have unlimited resources. We do have a good number of examples of the molybdenum case and also tungsten. So we do think they have more potential, and that somebody should pick that up, because there's a lot yet to be had with the molybdenum chemistry.
Okay, with that, we should probably end. From my perspective, it's been fabulous to be together with good friends and with Barry, if only remotely. And I wish all the best. I'm going to turn things over to Fiona and Alois for some final comments.
Yeah. Thank you, Gary. Maybe I can follow up.
May I make one comment about SOS?
Sure.
Because I think it's interesting. It is the successor to an earlier series, Hubenweil. And it was a question when I was on the editorial board deciding what should one do, the next edition of Hubenweil, or should one do something else, that it was the editorial board interacting with TIMA that they really should look to a new generation of these databases, because you have these computer techniques that could provide a easier way for people really to get information from these types of books. That Hubenweil is great, but it's not so easy to get the information. So it was really the advisory panel pushing on TIMA that got them to finally agree not to look for the next edition of Hubenweil, but to really get a fresh start. And it was really just great for them to take on this. This is a pioneering piece of work, having this kind of a database and putting it in place as TIMA has done has been remarkably productive. And so that they can be congratulated on. But it was the advisory panel that really pushed them in that direction.
Yeah, thank you for the comment. It's very true. I think it was a very pioneering step forward, and today that looks pretty obvious. But at the time, I think this was a really a step forward in publishing in general. Anyway, there's not a lot for me left to say, so except that I want to echo Gary, and I thought that this was a great event, and I personally enjoyed the presentations a lot, and I enjoyed very much the diversity of topics that we have been exposed to. And of course, it was no surprise in view of the speakers, the panel of speakers who we were able to recruit for this event, that this would be a great event for all of us. In particular, I'd like to thank Barry again, not just for taking the time to explain the details, but at the same time also for kind of drawing the bigger picture that we must not forget when we do science, when we do our science. And with this, I would like to thank all of you, of course, all the panel speakers and the panelists and all participants, and of course also TIMA for making this possible. And I'd like to hand over to Fiona for a final word. Fiona?
Sorry, yeah, just sharing my screen there, so hopefully you can see some of the slides. Okay, so yeah, I'd just like to say that we've experienced a wonderful symposium and gained an appreciation of the passion that the speakers today have for their field of organic synthesis, and I'm sure that this will be inspirational in many ways to the younger chemists out there. And indeed, despite the difficulties in 2020 for all of us because of COVID-19, this virtual symposium has presented us with a unique opportunity to share this moment together with Professor Trost and his former group members. I'd like to thank the symposium chair, Professor Gary Mollander, and Professor Forstner for his participation. I'd also like to thank each of the speakers, Professor Janine Cossy, Professor Nuno Maulide, Professor Mark Lautens, and of course, Professor Barry Trost. There has been a lot of work and preparation involved for everybody, so thank you very much for your time. I'd also like to, at this point, to thank all of the Science of Synthesis editors and authors worldwide who have made a huge contribution to the project over the last 20 years. And a big thanks to the SOS team, to Karen, Toby, Alex, Joe, Michaela, and Paul, Julie and the marketing team, and the rest of the TIMA chemistry team for all of the work behind the scenes, and indeed Nicholas and Vistaphone for the technical support tonight. So finally, a big thanks to all of you for listening today and attending. And if you have an interest in peer review and the new Select Crowd Review initiative from TIMA and FileStage, please note that the next TIMA web seminar will be on December 7th, together with Professor Ben List and Mail Fries. So stay safe and keep well. Thank you very much.